Hello there, and welcome to the Drift to the Stars. I'm so glad you found your way here tonight. Whatever you carried with you into this moment, the weight of the day, the thoughts that haven't quite settled, the small worries circling like moths near a lamp, you can set all of that down now. There is nowhere you need to be, nothing you need to solve. This is a place where curiosity moves slowly, where wonder arrives quietly, and where the universe has agreed, for a little while, to simply keep you company. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, if you're ready, let's begin. Somewhere far below the floor you're lying on, the earth is still burning. Not burning the way a fire burns, frantic, consuming, rushing toward its own end. This is a different kind of fire, patient, ancient, so deep that no drill has ever reached it, so old that it was already burning before the first living cell divided in the first warm ocean. It has kept its heat for 4.5 billion years without once going out. Picture the planet the way you might picture an egg, a thin, delicate shell on the outside, and something dense and warm held carefully within. The shell is the crust beneath your body. It is, in geological terms, nearly paper thin, and below it, the earth holds its inner warmth, the way a stone holds the heat of the afternoon sun long after the light has faded slowly, steadily, without effort. Scientists call this inner heat primordial. It is leftover warmth from the violence of formation, from the time when loose rocks and dust and gas collapsed into each other under the pull of gravity, and the whole collision released energy that the planet simply kept. 4.5 billion years of holding. 4.5 billion years of that same original warmth, still present, still circulating, still quietly at work. Even as you rest right now, that warmth is rising imperceptibly, slowly through miles of solid rock toward the surface. It will not reach you tonight. It will take millions of years to complete that journey. But it is moving. It has always been moving. And the volcanoes of the world are simply the places where that ancient patience finally, gently, arrives. The planet beneath you has never stopped tending its fire. There is a mountain on another world that makes every mountain on this one seem like a gentle fold in a tablecloth. On Mars, rising from a broad volcanic plateau, there is a volcano so wide that if you placed it over the eastern half of the United States, its edges would reach from one coast nearly to the other. And yet, standing at its base, you would not know you were standing at the base of a volcano at all. The slope is so gradual, so long, so slow, so patient in its rise that the whole mountain looks, from the ground, like a horizon, not a peak, a horizon. Picture walking its rim, not the mountain's base, the rim at the top, where the caldera waits, collapsed, and ancient, and enormous. That walk would take days, days of walking in a slow circle, with the thin Martian air around you and the rust-colored plains of an entire planet spread out below. You would cover more ground walking that single circle than you would walking across several of our largest countries. This volcano, whose name, Olympus Mons, carries the weight of myth, is no longer active. It sits in a kind of geological retirement, vast and still and cold. The eruptions that built it happened across hundreds of millions of years, each layer of lava adding almost nothing to its height, and yet, slowly, patiently, it became the tallest volcano known to exist anywhere in the solar system. It is a monument to what patience can make. Not force, not speed, just time and heat, and the slow accumulation of small things. What the universe builds slowly, it builds large. A river of lava moves at the pace of a thought you haven't quite finished yet. Most people, when they picture lava, picture something fast, something urgent and consuming, something you flee from. But the truth of lava, in most of its forms, is something far gentler. the kind that flows most often from shield volcanoes. The wide and quiet kind moves at a pace you could match with a calm, unhurried walk. Sometimes slower, sometimes slow enough that you could sit down beside it and watch it, and notice the way its surface darkens as it cools, going from bright orange to deep red to black, the skin hardening while the inside remains warm and flowing. Picture someone doing exactly that, sitting beside a slow lava flow in the early evening, watching the light change inside the moving rock. The surface wrinkles like fabric. It folds. It makes a sound like a soft crackle, like paper settling, like a fire finding its shape. And the whole thing moves, not rushing, not consuming, just going, following the slope of the land the way water does, the way all flowing things do, choosing the path of least resistance and taking it without hurry. This is how most of Earth's volcanic land was made. Not in catastrophe, in patience, in slow, warm accumulation, in rock that moved at walking pace and then stopped and cooled and became the ground someone would one day stand on. The island you might most associate with volcanoes, Hawaii, warm and green and impossibly beautiful, was made this way, slowly, flow by flow, step by quiet step. Most creation does not announce itself. It simply arrives. Right now, in the deep dark of the ocean floor, volcanoes are erupting where no human eye will ever see them. There are more volcanoes beneath the ocean than above it. Far more. Strung along the mid-ocean ridges, the vast underwater mountain ranges that circle the planet like the seams of a baseball. Thousands of volcanic vents breathe and pulse and release, completely unknown to the world above. No news report covers them. No satellite image captures them. They erupt in the cold and the dark and the pressure-heavy silence of the deep sea, and they have been doing so continuously for hundreds of millions of years. Picture the seafloor the way it actually looks in those places. Not sandy, not flat, but alive with structure. Towers of mineral-rich rock, fields of glassy black basalt, still warm from recent flows. Columns of shimmering water rising from vents, carrying heat upward into the cold. And everywhere, the slow work of creation. New seafloor being made, centimeter by centimeter, year by year, pushing older seafloor gently outward toward the continents, where it will eventually slide beneath them and return to the mantle from which it came. The ocean floor is not a resting place. It is a conveyor belt, a slow, planetary recycling system, driven by the same inner heat that has never gone out. Every piece of ocean crust that exists today will, given enough time, return to the deep earth and be remade. Nothing on this planet is finished. Everything is in the middle of becoming something else. And the ocean holds that process in its darkness, quietly, without any need for us to watch. An entire country is being stretched gently, almost tenderly, like warm dough pulled between two patient hands. Iceland sits directly on the mid-Atlantic ridge, which means it sits on the boundary between two of the great plates of the Earth's crust, the North American plate and the Eurasian plate, both of which are moving, almost imperceptibly, in opposite directions. And Iceland, caught between them, is slowly being pulled apart. The island grows a little wider every year, not by much, about the width of a human fingernail in 12 months. But every year, in the southwest of Iceland, you can walk between the two plates. There are parks built along the rift-long, quiet valleys, where the ground has dropped slightly as the two sides have separated, leaving a visible seam in the earth, a geological wound that is also, somehow, a geological gift. Visitors walk down into these valleys and stand at the bottom and look up at walls of rock on either side, knowing that one wall belongs to one continent and the other wall belongs to another, and that the space between them was not there 1,000 years ago. The land beneath their feet is new, younger than many cities, made from lava that filled the gap as the plates separated, as if the earth could not bear to leave a space unfilled, and sent up fresh rock to close the distance even as the distance kept growing. Iceland is volcanic and alive and perpetually, slowly, coming apart and becoming more itself in the process. Some things grow by letting go. There is a stone that has been here since almost the very beginning, and it has been waiting quietly ever since. The oldest volcanic rocks ever found on Earth are fragments of the original crust formed when the planet was so young. It had no oceans yet, no continents in any shape we would recognize, no life of any kind, just heat and the slow cooling of a surface that had recently been entirely molten, and the first dark rocks appearing like islands of stillness in a world that was still deciding what to become. Some of these ancient fragments have survived billions of years of geological recycling, carried along by plate tectonics, buried, compressed, altered, and yet somehow preserved. Geologists find them in the hearts of ancient cratons, the stable, ancient cores of continents that have been geologically quiet for so long they have become like keepsakes, places the Earth seems to have set aside and not disturbed. Imagine holding a piece of rock that formed before there were any shells on any shore, before there were shores, before the ocean existed in its current form. The rock itself is dark and dense and unremarkable in appearance. It does not look like a relic. It looks like a rock, and that, somehow, makes it more extraordinary, not less. It has been here through every extinction, every ice age, every moment in the vast unfolding story of this planet. It has been here through all of it, quietly, asking nothing, needing nothing. Some witnesses do not speak. They simply remain. The wind, on certain volcanic shores, collects lava into something that looks like spun gold. When lava fountains high enough into the air, as it sometimes does from the vents of Hawaiian volcanoes, thrown upward in thin, bright threads, the wind catches those threads while they are still molten and stretches them, cools them, carries them, and they fall, not as rock, but as glass. Fine, golden, hair-thin filaments that drift on the breeze and settle across the landscape like the world's most delicate textile. They are called Pele's hair, after the Hawaiian goddess of volcanoes, and they look, genuinely, like hair long, soft-seeming, glinting in the light. You would almost want to touch them, though they are fragile enough that the warmth of a hand would damage them. They are made of the same basaltic glass as obsidian, but drawn so thin by the wind that they become translucent, and in certain angles of light they glow. Picture a lava field after a night of fountaining, the dark rock dusted with these golden threads, lying across everything the way frost lies across a morning field, delicate, unexpected, made by processes that do not know they are making something beautiful. This is the Earth doing something it was not, in any purposeful sense, trying to do. The lava was simply rising, the wind was simply blowing, and between them, without intention, something lovely arrived. The universe makes beauty the same way it makes everything else, by following its own nature and not stopping. On a moon of Jupiter, the volcanoes never rest. Io, Jupiter's innermost large moon, caught in the gravitational pull of the largest planet in the solar system, is the most volcanically active body we have ever found. Not active the way Earth is active, with volcanoes that sleep for centuries between eruptions. Active the way a heart is active, constantly, without pause, with eruptions happening somewhere on its surface at almost every moment we have ever looked at it. The reason is gravity. Jupiter is so massive that its gravitational tug on Io and the competing tugs of Io's neighboring moons flexes and squeezes the moon the way your hands might squeeze a stress ball. That flexing generates heat, and that heat has nowhere to go except up and out, through the surface, through the hundreds of volcanic vents scattered across Io like pores. The result is a surface that is perpetually being remade. Lava flows covering older lava flows, calderas collapsing and refilling. The entire surface of the moon resurfaced, geologists estimate, every few hundred years. Whatever markings or craters might have formed, they are buried almost immediately under fresh volcanic rock. Io has no memory, in a geological sense. It cannot hold onto its own past. It is always, only, now. Seen from space, it is yellow and orange and red sulfur-colored. Strange, a little like a bruised moon, a little like a painting made by someone with no interest in subtlety. And all of that color, all of that restless remaking, happens in silence. In the vacuum of space, beautiful and constant and entirely alone. Even restlessness, at a great enough distance, looks like stillness. Some mountains have been sleeping longer than civilization has existed. A dormant volcano does not die. It rests. And the difference between those two things is everything. Inside a dormant volcano, the magma chamber may still hold heat, still hold pressure, still hold the slow memory of what it is simply waiting, the way seeds wait in dry soil, with no urgency and no deadline. Some of these sleeping mountains have been quiet for 10,000 years, 20,000, longer than writing, longer than agriculture, longer than any story we have told about ourselves. Picture a mountain so old in its sleep that entire civilizations have risen and fallen on its flanks. People have built villages there, planted vineyards, buried their grandparents in its soil. The mountain has become, in the minds of everyone who lives near it, simply a mountain, a shape on the horizon, a backdrop to a life, something so permanent it no longer seems geological at all. It seems inevitable, it seems eternal, and yet beneath it, quietly, the heat persists. The rock stays softer than the rock around it. The ground, if you know how to listen, still speaks in whispers, small tremors, faint gas emissions, the barely perceptible breath of something that has not ended, only paused. Scientists who study dormant volcanoes speak of them the way you might speak of someone in a very deep sleep, carefully, with attention, with the understanding that stillness and absence are not the same thing. There is a kind of patience in the earth that has no human equivalent. It does not count the years. It simply holds. Before there was weather, there was steam. The oldest sound the atmosphere has ever known is not wind, not rain, not thunder. It is the hiss of volcanic steam, rising from a vent in newly cooled rock water vapor, released from magma meeting the surface for the first time, curling upward into an air that did not yet have clouds. This sound was happening on Earth before the oceans were full, before rain existed, before any living thing had ears to hear it. Even now, volcanic vents produce that same sound. Stand near a fumarole, a crack in the earth through which volcanic gases escape, and you hear it clearly. A low, continuous exhale, warm, slightly sulfuric, ancient in a way that bypasses thought and goes somewhere deeper, somewhere that recognizes the sound not from memory but from something older than memory. Picture the early Earth, 4 billion years ago, a surface still hot enough to glow in places, covered in volcanic vents releasing steam into a sky that looked nothing like ours. That steam rose and cooled and fell. It rose and cooled and fell again. Over millions of years, the accumulation of that falling, that first volcanic rain, filled the basins of the world with water. The oceans did not arrive from space, as was once thought. They condensed from volcanic breath. They were exhaled into being. The water in every ocean, in every cloud, in every glass, on every bedside table arrived here through the same slow process, through heat and steam and the patience of falling. You are, in some small and genuine way, made of the Earth's first breath. Deep in the Pacific, the seafloor is covered in shapes that look like something gently dreamed. When lava erupts underwater, not in the scalding shallows but in the true deep ocean, under miles of cold pressing water, something remarkable happens to its shape. The pressure of all that water prevents it from exploding outward the way surface lava sometimes does. Instead, it oozes. It pushes out slowly from the vent, and as it meets the cold water, Its outer surface instantly solidifies into a skin, while the inside stays molten and keeps pushing forward. The result is a rounded, bulging form, a pillow, and then another, and another, until the seafloor is covered in smooth, rounded forms, stacked and settled together, looking almost soft. Pillow basalt, geologists call it. And photographs of it, taken by submersibles descending into the dark, do look remarkably like pillows. Dark grey-green, rounded, nested against each other in comfortable-looking arrangements. The deep sea lit only by the submersible's lights, and across the floor, these gentle forms, cooling quietly in the pressure and the cold. This is how much of the ocean floor was built. Not in explosions, but in slow, rounded accumulation. Form after patient form, each one cooling and settling before the next arrived. Even as you rest right now, somewhere in the deep Pacific, a new pillow is forming. The lava is pushing out, finding its shape, cooling into something that will lie on the seafloor for millions of years, before plate tectonics eventually carries it back into the mantle. The ocean floor is covered in the Earth's oldest pillows, and everything is resting on everything else. Beneath a famous park in the American West, something ancient and enormous is breathing very slowly. Yellowstone sits above one of the largest magma systems on the continent, a vast reservoir of partially molten rock that has been feeding eruptions, geysers, and hot springs for millions of years. The ground in parts of Yellowstone rises and falls by inches over years, not because of earthquakes, but because the magma below is shifting, expanding slightly, contracting slightly, moving in rhythms that operate on timescales far longer than a human life. The caldera, the collapsed remnant of the last great eruption, which happened long before any human stood on this continent, is so large that early visitors to the park did not realize they were standing inside it. It looks, from the ground, simply like a broad valley, ringed by gentle hills. Only from above, from maps and satellite images, does the shape become clear. Only from a distance does the truth of the scale reveal itself. Scientists monitor Yellowstone with extraordinary care seismometers, GPS sensors, tilt meters measuring the ground's angle with almost impossible precision. Not out of fear, but out of curiosity. Out of the same impulse that makes you want to understand something you love. And what they have found, across decades of watching, is that Yellowstone is not building toward anything urgent. It is simply alive. Quietly, slowly, enormously alive beneath a landscape of hot springs and bison and early morning mist. The ground you might stand on there feels perfectly solid. And it is solid. It is also, below that solidity, in motion. Most things that hold us are also, in their own way, moving. There is a kind of rock that could cross an ocean by simply floating. Pumice forms when magma, rich in gas, erupts so quickly that the gas cannot escape. It becomes trapped inside the cooling rock as millions of tiny bubbles, making the rock more air than stone. The result is a rock so porous, so shot through with emptiness, that it floats. Not for a moment, not barely. It floats the way wood floats, or foam indefinitely, for years, for decades, drifting wherever the currents take it. After large volcanic eruptions near the ocean, pumice rafts have formed that cover miles of sea surface. Not a thin, scattering, thick accumulations of floating rock, pale grey and rough-textured, bobbing together in the swell. Ships have sailed through them and reported that the ocean appeared to have turned solid, that the horizon became a flat, pale field, stretching in every direction. And on those rafts, life travels. Barnacles attach. Small crabs find purchase. Microorganisms colonize the surfaces. Seabirds land and rest. In this way, pumice rafts become mobile ecosystems, tiny, temporary arcs made from volcanic rock, carrying passengers across the ocean to islands they might never have reached any other way. It is thought that some of the biological richness of remote Pacific islands arrived this way. carried by floating stone from one shore to another. Life using the volcano's aftermath as a vessel. The Earth finds ways to distribute its gifts. Even its lightest rock becomes a bridge. When a great eruption happens, the atmosphere itself begins to ring like a bell. The largest volcanic eruptions release energy on a scale that the air around the planet cannot simply absorb. Instead, it transmits it as waves. Infrasound waves, too low for human ears to detect, that travel outward from the eruption in every direction, moving through the atmosphere at the speed of sound, circling the planet once, and then again, and then again, like ripples on a pond. Except the pond is the sky, and the ripples take hours to complete each circuit. When Krakatoa erupted in 1883, barometers around the world, instruments measuring air pressure, sitting on shelves in observatories from London to Sydney, registered the passing of these waves for days afterward. Scientists at the time did not fully understand what they were seeing. They noted the anomaly. They recorded the numbers. It was only later that the pattern became clear. The atmosphere had rung, and the ringing had traveled around the entire Earth multiple times before fading. More recently, when Hunga Tonga erupted in 2022, the same thing happened. The same patient, planetary ringing, the same slow waves, circling and circling, detected by instruments on every continent. Think of the atmosphere not as a layer of air, but as a membrane, vast, continuous, connected at every point to every other point. What happens at one location on that membrane sends a signal that eventually, slowly, arrives everywhere else. Every great exhalation of the Earth reaches the whole sky. Nothing erupts in isolation. There are fields of volcanic soil so fertile that farmers have been returning to them for 1,000 years. The same eruption that destroys also, over time, gives back. Volcanic rock weathers differently from other rock. It breaks down relatively quickly, by geological standards, releasing minerals into the soil that plants find extraordinarily nourishing. Potassium, phosphorus, calcium, magnesium, the periodic table of what life needs, locked inside the basalt, slowly freed by rain and wind and the acid of roots. The soils on the slopes of volcanoes in Italy, in Java, in the Philippines, in Central America, some of the most productive agricultural land on Earth, are volcanic soils, dark and deep and rich. Farmers on the flanks of Vesuvius have grown grapes there for 2,000 years, not despite the volcano. Because of it, the mountain that buried Pompeii is the same mountain that has been feeding people quietly ever since. Picture a terrace carved into a volcanic slope, the soil dark and loose, turned by generations of hands, planted with the same varieties of grape or olive or wheat that were planted there by someone's great-great-grandmother's great-great-grandmother. The mountain rising above, dormant, snow on its upper reaches in winter, and below, the tended rose, the patient work of people who understood, instinctively, the gift inside the danger. Volcanic soil does not forget what made it, and the people who farm it do not forget either. Some gifts take a very long time to arrive, but they are worth the waiting. Even now, beneath the places we have named and mapped and walked across 1,000 times, the planet is listening to itself. Seismologists have developed instruments sensitive enough to detect the movement of magma miles underground, not the dramatic shaking of an earthquake, but something quieter, a low, rhythmic tremor, a vibration in a frequency so slow and so deep that it is almost more feeling than sound. They call it volcanic tremor, and it is distinct from any other signal the Earth produces. It has its own signature, its own voice, and what it is, translated into something human, is the sound of a fluid moving through rock, of magma finding its way upward through fractures and channels, pressing forward with the gentle persistence of something that has all the time in the world. The planet, in these moments, is not silent. It is speaking in registers we have only recently learned to hear. Picture a scientist in a monitoring station, headphones on, listening to a spectrogram scroll across a screen, the visual record of the Earth's own murmur, not alarmed, attentive. The way you might listen to the breathing of someone sleeping beside you, not waiting for something to go wrong, but simply present to the fact of their aliveness, simply glad to be near something living. The Earth has always been making this sound. We simply did not have the instruments to hear it. Some conversations have been waiting a very long time for someone to listen. Not every volcano announces itself with fire. Some volcanoes do nothing more dramatic than sigh. They release gentle columns of steam from their summits, pale, quiet, drifting upward into whatever sky is waiting above them, and that is all. No lava, no ash, no trembling of the ground beneath nearby towns. Just the slow, warm exhalation of water heated deep inside the earth, rising through fissures in the rock and arriving at the surface as vapor, as mist, as something that looks more like breath than eruption. These are called solfataras, or fumarolic fields, places where the volcanic system beneath is active enough to heat groundwater and release gases, but not active enough, or not positioned correctly, to produce anything more. They hiss softly. They smell of sulfur, that ancient mineral smell that somehow feels primordial, like the earth reminding you what it is made of beneath the grass and soil. And they steam year-round, in every season, in sun and rain and snow alike, indifferent to the weather happening above them. There is one such field in Italy, Solfatara, near Naples, that has been steaming continuously for recorded human history. The Romans knew it. They wrote about it. They built roads near it and visited it as a curiosity, a place where the earth seemed to breathe. 2,000 years of recorded sighing from the same patch of ground. Picture standing at the edge of that field in the early morning, when the surrounding air is cool enough that the steam becomes visible immediately, rising in soft columns against a pale sky. The ground warm underfoot, the hiss low and constant. The earth has been exhaling here since before anyone thought to write it down. It simply continues. The iron in your blood has traveled further than any map can show. It was forged in the core of a star that no longer exists, that burned and collapsed and scattered its elements outward into space billions of years before our sun ignited. That iron drifted through the galaxy in a cloud of gas and dust. Gravity gathered it. The young Earth collected it, and the planet, through its own internal chemistry, concentrated iron at its core, pulled it downward by density, by weight, by the simple preference of heavy things for the center. But iron did not stay, only at the core. Volcanic processes carry it upward, into the mantle, into the crust, into the basaltic rock that forms ocean floors and volcanic islands. Rain and rivers dissolve it slowly from that rock. Plants absorb it from soil. Animals eat the plants. And somewhere, in that long, patient chain of transformation, star to space, to planet, to rock, to soil, to root, to leaf, to food, to body, the iron arrived in you, in the hemoglobin of your blood, in the molecule that carries oxygen from your lungs to every cell that needs it. Right now, as you breathe slowly towards sleep, iron that was forged in a dead star is moving through your body, doing the quiet work it has always done. Volcanic rock is one of the chapters in that story. Not the first, not the last, but a chapter without which the story would not reach you. You are not separate from this geology. You are downstream of it. Where the ocean meets new lava, something neither solid nor air is born. When an active lava flow reaches the coast of a volcanic island and slides into the sea, the meeting of two ancient elements, molten rock and salt water, produces something geologists have named with a word that sounds almost like a whisper: laze. A portmanteau of lava and haze. And that is exactly what it is. A fine, white, softly billowing cloud of steam and tiny glass particles and trace gases rising from the shoreline where the rock enters the water. From a distance, it looks beautiful. A soft white veil drawn along the coast, drifting with the wind, catching the light. Up close, it is something more complex, a boundary where two enormously different systems are meeting and negotiating, exchanging heat, creating new chemical compounds that did not exist a moment before. The shoreline itself changes constantly during these events. New land forms black and jagged and still warm, extending the island out into the sea. Ground that did not exist last week. Ground that no foot has ever touched. Still too hot. Still cooling. Still deciding what shape it will hold. In Hawaii, people sometimes gather at a respectful distance to watch this happen, to watch land being born. They stand quietly at the edge of the old shore and look out at the new one forming in the water. The steam rises. The rock hisses and clicks as it cools. The island grows, imperceptibly, outward. Creation does not always happen in the past. Sometimes it is happening right now, at the edge of the water, in the last light of the afternoon. A caldera does not fall. It settles slowly, and with a kind of geological grace. When the magma beneath a volcano empties, whether through eruption or through slow draining back into the earth below the roof of the magma chamber, loses its support, and the ground above it, without anything to hold it up, begins to descend. Not catastrophically, in most cases, not all at once, but in stages, over hours or days, or sometimes longer. The surface lowers itself into the space below, the way a mattress slowly conforms to the weight of a body settling into sleep. The result is a caldera, a broad, roughly circular depression, often miles across, with gently sloping walls and a floor that sits lower than the surrounding landscape. Some calderas fill with water over time, becoming lakes of extraordinary beauty and stillness. Crater Lake in Oregon sits inside a caldera formed thousands of years ago, its waters so deep and so clear and so still on calm days that it appears to be the sky itself folded into the earth. Others fill with new volcanic activity, small cinder cones forming on the caldera floor, the volcanic system rebuilding itself from the inside out with the same patience it used to empty itself. And some calderas simply rest, wide and quiet, open to the sky, holding weather inside them the way a bowl holds water, collecting morning cloud, filling with snow in winter, warming in summer sun, becoming, over centuries, a landscape so gentle it is difficult to imagine what made it. What empties can also hold. What collapses can also become a place of stillness. The Pacific Ocean is ringed by a chain of becoming that never stops. Most people know the Ring of Fire by its name, and the name suggests danger, suggests the edge of something, suggests a boundary to stay away from. But standing anywhere along its arc and looking outward, what you feel is not danger. What you feel is the particular quality of a place where the earth is awake, where the ground has not finished deciding what it will be, where the geological story is still very much in progress. The Ring of Fire follows the edges of the Pacific Plate, a vast section of ocean floor, that is, along its margins, sliding beneath the surrounding continents or colliding with them, and that collision produces volcanoes, hundreds of them, stretching from the southern tip of South America, up through Central America and the western United States, across Alaska and the Aleutian Islands, down through Japan and the Philippines and Indonesia, and around through New Zealand. Hundreds of millions of people live along this arc, not despite its geology but woven into it. The soils are rich. The fishing is extraordinary. The landscapes are dramatic and varied and alive. The cultures that developed there often understood, in ways both practical and spiritual, that they were living on something active, something breathing, something that required relationship rather than conquest. The Ring of Fire is not a ring of endings. It is where the planet most visibly continues its own long work. Some edges are not boundaries. Some edges are simply where the making happens. A new island appeared from the ocean once, in living memory, and people watched it arrive. In 1963, off the southern coast of Iceland, fishermen on a trawler noticed something that did not belong on the ocean's surface. Not a ship, not a reef, not a disturbance of weather. Smoke, rising from the water, and then, within hours, something solid beginning to appear above the surface. A dark mass, steam-shrouded, growing slowly visible through the haze. The island of Surtsey was being born. Over the next 3.5 years, the eruption continued. The island grew not smoothly, not steadily, but with volcanic irregularity, sometimes larger, sometimes losing ground to the waves that constantly worked at its edges. Eventually, the lava flows hardened enough that the sea could not easily take them back. The island stabilized. It reached its maximum size. And then the eruption ended, and the island sat, new and black and bare, in the cold North Atlantic. Scientists declared it a natural laboratory and restricted human access almost immediately. They wanted to watch what happened, how life would arrive, how it would establish itself on ground that had never existed before. The first living things were bacteria, carried by wind and wave, then mosses, then seabirds, which brought seeds in their feathers and nitrogen in their droppings. Within decades, the island had soil. Within decades, it had plants. Life did not wait for an invitation. It simply arrived as life does, wherever there was ground to stand on. The island is still there, slowly eroding now, slowly returning to the sea. It had its moment of rising, and now it is taking its time going back. Even islands have their arc. The longest silences in geology belong to the places that have said the most. Lava tubes form when the outer surface of a lava flow cools and hardens, while the molten rock inside continues to move. And then, when the flow ends and the liquid drains away, what remains is a tunnel. A hollow channel in the rock, sometimes small enough that you move through it on your hands and knees, sometimes large enough to drive a vehicle through, sometimes stretching for miles beneath the surface of an island or a plain, invisible from above, mapped only by the patience of cavers descending into darkness. Inside a lava tube, the silence is not ordinary silence. It is the silence of a space that was made by moving rock and then abandoned by it, a space that has been still, in some cases, for tens of thousands of years. The walls are smooth where the lava surface flowed, and rough where it dripped and cooled. In places, formations called lavasicles hang from the ceiling lava's version of stalactites, formed when molten rock dripped and froze in mid-fall. Some lava tubes on the Moon and on Mars have been identified by satellite dark openings in the surface that descend into tubes large enough to shelter structures, perhaps large enough one day to shelter people. The same geological process that created quiet tunnels beneath Hawaii has been creating quiet tunnels on other worlds. Even as you rest right now, there are tunnels beneath volcanic islands that have not been entered in thousands of years, dark and still and cool, holding their silence the way a held breath holds itself, not forever, but with patience. The earth makes rooms, and then it waits to see who will find them. Some places on earth exist for only a little while, and their brevity is part of what they are. A volcanic island rising from the seafloor is born into a kind of countdown. The moment it breaks the surface, erosion begins. Waves working at its edges, rain dissolving its rock, the weight of its own mass, slowly pressing the ocean floor beneath it downward, as the oceanic crust cools and contracts. The island is beautiful and new and already, in the most patient of geological senses, on its way back. The Hawaiian Islands are the most visible example of this arc. The Big Island, the youngest, is still growing, still being added to by active lava flows. Maui is older, its volcanoes dormant now, its edges gentler. Oahu older still. Kauai, the oldest of the main islands, worn by millions of years of rain into something extravagantly green and soft, its volcanic origin almost hidden beneath the lushness that covered it. And northwest of Kauai, stretching across the Pacific in a long chain, are the older islands, worn down now to low atolls, to barely their rings of sand and coral, to shallow places in the ocean where an island used to be. The chain tells the whole story if you follow it in the right direction. Birth, growth, dormancy, erosion, return. Every island in the chain was once the youngest. Every island was once where the lava was flowing. There is something quietly comforting in a story that moves in one direction, slowly, without hurrying, toward a return to the deep. All things complete their arc, and the ocean is patient enough to receive them. Sound, given enough reason, will carry itself across the world. In August of 1883, the eruption of Krakatoa produced an atmospheric pressure wave so powerful that it was recorded by barometers on every continent. But the sound itself, the actual acoustic event, the concussive wave of compressed air, traveled outward from the eruption site and was heard, clearly and unmistakably, nearly 5,000 kilometers away. On the island of Rodrigues, in the Indian Ocean, people reported hearing what they described as distant cannon fire. They went to their windows. They looked at the horizon. There was nothing there, only the sound, arriving from somewhere impossibly far. That sound had been traveling for hours before it reached them, moving at the speed of sound through the atmosphere, crossing ocean after ocean, arriving finally at a small island where no one had any reason to be listening for it and announcing itself anyway, quietly, like a letter delivered very late, from very far away. We have grown accustomed to thinking of sound as a local thing, something that happens in a room, on a street, between people who are near each other. But the atmosphere does not think in those terms. It is continuous, connected at every point. A disturbance at one location is, eventually, a disturbance everywhere. The people on Rodrigues who heard what they could not explain were not imagining things. They were simply standing at the far end of the longest sound a volcano had sent into the world in recorded history. Some things reach you from a distance you cannot fathom, and they are real. A tree can survive what it cannot outrun by simply being where the lava is not. When lava flows through a forest, it does not flow evenly. It follows the land, the low places, the gullies, the gradual slopes. And sometimes the flow splits around a rise in the ground, or a cluster of large trees standing on slightly higher terrain, and the lava passes on either side and continues downhill, leaving behind a small island of untouched forest, surrounded entirely by new black rock. These islands are called kipukas in Hawaiian, a word that means, roughly, a place of refuge or a window into the past, and they are extraordinary places. The forest inside a kipuka is old. It existed before the lava, and it exists after. It holds species that cannot survive in the new volcanic terrain, that need the old soil and the old shade, and the old complex web of relationships that take centuries to develop. In a landscape of new black rock, stretching in every direction, the kipuka is a living archive, a piece of the world that was preserved by the accident of topography. Scientists study kipukas carefully because they offer something rare in ecology, a controlled comparison. Same climate, same elevation, same species pools, but different histories. The kipuka tells you what the forest was. The surrounding lava field tells you what is coming. Slowly, as the rock weathers and soil begins to form and life begins its long work of recolonization. Even as you rest right now, there are old trees standing in the middle of lava fields in Hawaii, untouched, surrounded by rock that flowed around them like water around stones in a stream. Some things are spared not by strength, but by where they happen to stand. Inside a piece of volcanic rock, there is air that has not been breathed since before humans existed. When lava cools quickly enough, it traps gases, volcanic gases, atmospheric gases, the chemistry of the air at the moment of eruption, inside tiny sealed pockets within the glass of the rock. Fluid inclusions, geologists call them, and those inclusions are time capsules, sealed the moment the rock solidified, unchanged since, holding within them a sample of the world as it was in that exact moment, that exact eruption, that exact ancient afternoon. Scientists extract these inclusions with extraordinary care, grinding samples under controlled conditions, capturing the released gases, analyzing their composition, and from them, they read the atmosphere of the past. Not an approximation, not a model, the actual chemistry, the actual air. Samples from ancient eruptions have revealed things about the early atmosphere that could not have been known any other way. The ratios of gases, the temperatures, the conditions that existed before any human, or proto-human or pre-human, stood anywhere on the surface of the Earth. Picture holding a piece of volcanic glass up to the light. It is dark, almost opaque, smooth where it was fire-polished as it cooled. Inside it, invisible, sealed into structure of the silica, is air from a world that no longer exists. A world that was this world, but earlier, before the ice ages, before the mammals, before the forests as we know them. The rock is a library, each sealed pocket a word, each ancient eruption a page. We are only just learning to read it. The moon carries its own volcanic history, dark and frozen and vast. When you look at the full moon, really look at it. At the dark regions spread across its face, you are looking at ancient lava. The dark areas visible to the naked eye from Earth are called Maria, from the Latin word for seas. Early astronomers thought they might be oceans. They are not oceans. They are plains of basaltic lava, formed between 3 and 4 billion years ago, when the moon was young enough to still be volcanically active, when its interior still held enough heat to produce eruptions that flooded its low-lying basins with dark, thin, freely flowing rock. And then the heat faded, the eruptions slowed, and the lava froze in place, where it has remained ever since, undisturbed by wind, by rain, by the slow processes of erosion that constantly rework the surface of the Earth. The lunar Maria look today almost exactly as they looked 3 billion years ago. Footprints left there 50 years ago by astronauts are still there, unchanged. The lava plains are still there, smooth and dark and patient. There is something deeply settling about that, about a volcanic landscape so perfectly preserved that it exists as a record of what the inner solar system looked like in its early youth. The moon did not choose to remember. It simply had nowhere to forget. Every time you look up at a full moon on a clear night, you are looking at volcanic rock, ancient, frozen, quietly facing the Earth across the dark. The sky above you holds its own geology, and it has been there every night you have ever slept. There are volcanoes on Earth so gentle they are measured not in eruptions, but in breaths. A fumarole field in the highlands of Iceland, or in the geothermal valleys of New Zealand, or in the volcanic backcountry of Japan, does not look, at first, like something volcanic at all. It looks like a meadow that is somehow also a kitchen. Steam rising from cracks in the ground. The smell of minerals in the air. The ground warm and soft underfoot in places, crusted and pale in others, where the gases have deposited sulfur and silica over centuries of slow accumulation. These fields exist where volcanic heat reaches close enough to the surface to interact with groundwater, but not close enough to produce eruptions. They are the volcano's quietest register, its most habitual mode, and they are ancient. Some of them have been steaming in the same locations for thousands of years, long before anyone built a road nearby, or a research station, or a tourist path with careful wooden walkways leading visitors through the steam. In Japan, the tradition of onsen hot spring bathing grew from exactly this volcanic gentleness. The same heat that, deeper and more concentrated, drives eruptions, arrives at these springs in a form that is warm and mineral-rich, and, by long tradition, restorative. People have been lowering themselves into volcanically heated water for as long as there have been people near these mountains. The volcano, at its quietest, becomes a gift so mild it feels like comfort. Not all power announces itself. Some of it simply warms the water and waits. There are lakes on Earth so still so vivid, so chemically singular, that they exist in a category of their own. Some volcanic craters fill with water over time, rainfall gathering in the bowl of an old eruption, with no outlet, only slow evaporation at the surface and slow seeping through the rock below. And in some of these crater lakes, the water is not the blue-gray of an ordinary lake. It is something else entirely, turquoise, vivid and tropical and almost unnatural looking, like something from a painting made by someone who had never agreed to be subtle. The color comes from chemistry. Volcanic gases, sulfur dioxide, carbon dioxide, hydrogen sulfide, dissolve into the water, making it acidic, and the acidity interacts with dissolved minerals to produce compounds that scatter light in particular ways. Some crater lakes are acidic enough to dissolve metal, and yet they are beautiful, genuinely, specifically, profoundly beautiful. The kind of beautiful that stops conversation. Kelimutu, in Indonesia, has 3 crater lakes sitting close together at its summit, and each one is a different color, colors that shift over years as the volcanic chemistry beneath them changes. Turquoise, brown, black, red. The lakes do not coordinate. They simply change, independently, according to what the earth is doing below them, and the result is something that looks intentional, considered, as if someone were making choices about color. No one is making choices. The chemistry is making choices, and somehow that makes it more beautiful, not less. In the old stories, the fire in the mountain was not a disaster waiting to happen. It was a presence. Ancient Hawaiians understood Kilauea not as a geological feature, but as the home of Pele, the goddess of volcanoes, of fire, of creation, and destruction held together in one figure. She was not feared in the way a disaster is feared. She was respected the way a powerful relative is respected, offered to, spoken of carefully. Her movements, her lava flows, her eruptions were understood as expressions of her will, her mood, her grief, or her abundance. This relationship between people and volcanic landscape shaped everything the stories told to children at night. The protocols observed when lava approached a village, the way loss was understood when a home was covered by a flow. It was not meaningless destruction. It was Pele moving through the world. And Pele, in the tradition, also gave back the rich soil, the new land. The islands themselves were her gifts. Other cultures around volcanic mountains developed similar relationships. The people of the slopes of Mount Merapi in Java, of Etna in Sicily, of Popocatépetl in Mexico, all developed ways of living with the mountain that involved relationship rather than simply risk management. The mountain was something you knew, something you had always known, something your grandparents had known, and their grandparents before them. There is a kind of wisdom in that orientation, in knowing that you live alongside something powerful and choosing relationship over distance. The mountain has always been there. It was here before the first person named it, and the naming, when it came, was an act of recognition. We did not discover these mountains. We introduced ourselves to them. Beneath the frozen continent at the bottom of the world, something warm has been burning in the dark for longer than we have known about it. Antarctica is not only ice. Beneath miles of glacial sheet, beneath the compressed cold of millions of years of snowfall, the continent holds volcanic features that have been active quietly, persistently, for geological spans of time. Mount Erebus, the southernmost active volcano on Earth, sits near the coast and has maintained an active lava lake in its crater for as long as scientists have been watching it. A lava lake that glows faintly in the polar dark. A lake that occasionally throws up small eruptions of lava bombs that land on the crater rim and cool into strange, twisted shapes. But beneath the ice sheet, further inland, there are volcanic features that no one has ever seen directly inferred from the heat they release, from the way they affect the ice above them, from the meltwater lakes that form beneath the glacier where the heat is concentrated. Subglacial lakes, liquid and dark, and cut off from the surface by miles of ice. They have their own ecosystems, bacteria living in complete isolation, in water that has not contacted the outside world in hundreds of thousands of years. Picture that space, the absolute darkness, the weight of the ice above, the warmth rising from the volcanic rock below. And in that warmth, in that darkness, in that isolation, life. Small and slow and patient, but life. Doing what life does, which is to find the conditions it needs and to continue, even in the coldest place on Earth. The planet's inner warmth creates a space where something can live. The fire beneath the ice has never gone out. It simply goes unnoticed. Lava, when it comes to rest, does not simply stop. It composes itself. The Paheho flows of Hawaii, that word pronounced with the same gentle rhythm it describes, Pahoihoi, are among the most quietly beautiful surfaces geology produces. When low-viscosity lava moves slowly enough and cools gradually enough, its surface does not break into the sharp, jagged rubble of other lava types. Instead, it folds, it wrinkles. It forms long, smooth ropes of rock that curve and overlap and interweave across the landscape, like the surface of something kneaded by enormous, patient hands, walking across a Pahoho field carefully, slowly, because even old flows can be uneven underfoot, is walking across a record of movement frozen mid-gesture. Every fold is a moment captured. Every rope of rock is the path the lava chose, the speed it was moving, the temperature it held at that exact second before the surface hardened and held. It is a landscape of decisions, each one permanent, each one made without deliberation. The colors shift across the surface: black, where the basalt is fresh and unweathered; reddish-brown, where iron has begun to oxidize; pale gray-green, where the first lichens have arrived and begun their slow work of turning rock into something a root might find useful. And sometimes, in shallow depressions in the rock, small pools form when it rains clear water on black stone, the sky reflected in miniature. Even as you rest right now, Paheho surfaces on the big island of Hawaii are doing nothing at all, simply lying in the sun, simply being what they became. There is a kind of peace in a surface that has finished moving, that has found its final form and settled into it completely. The floor of every ocean is younger than the continents that surround it. This seems, at first, counterintuitive. The ocean is ancient. It has been here, in some form, for nearly 4 billion years. And yet the rock that currently forms the seafloor is nowhere older than about 200 million years. The continents hold rocks 3 and 4 billion years old, ancient and stable and largely unchanged. But the seafloor is perpetually, quietly renewing itself. The reason is the same volcanic engine that drives everything. At the mid-ocean ridges, new seafloor is constantly being created from upwelling magma. And at the ocean's edges, the old seafloor is sliding beneath the continents, subducting, returning to the mantle, being remelted and recycled. The ocean floor is a conveyor belt that has been running, without interruption, for hundreds of millions of years. What this means is that the seafloor you might imagine as permanent, solid, unchanging, the true bottom of the world, is actually the most recently made surface on the planet. It is younger than the dinosaurs, younger, in the oldest parts, than the first flowering plants. The continents are the elders here, the ancient ones, standing at the edges while the ocean floor endlessly remakes itself in the middle. Picture the planet viewed from above the Pacific, watching at a speed that compresses millions of years into minutes. The seafloor spreading outward from the ridges like slow wings, the continents holding steady at their edges, old and patient and permanent. The oldest things here are the ones that did not move, and the newest things are constantly arriving from below. Some of the air you are breathing was made by a volcano. Not the air, as it is now rich in oxygen, blue with nitrogen, the particular mixture that life on Earth has both inherited and produced. The very early atmosphere, the one that existed before photosynthesis, before plants, Before any organism that processed sunlight, that atmosphere was largely volcanic. Carbon dioxide, water vapor, nitrogen, sulfur dioxide. The gases released by eruptions over hundreds of millions of years, accumulating in an atmosphere with nowhere else to go, building up into something thick and warm, and utterly unbreathable by anything alive today. And then, life changed it. Slowly, over billions of years. Photosynthetic organisms, simple, ancient, oceanic, began converting that volcanic carbon dioxide into oxygen, releasing it into the air as a byproduct. The way you release carbon dioxide as a byproduct of breathing. One was making the atmosphere the other would need, not in cooperation, not in planning, but in the simple way that chemical processes respond to conditions. The oxygen you are breathing now is the accumulated exhalation of billions of years of life converting a volcanic atmosphere into a living one. The volcanoes made the first air. Life remade it into the air that made more life possible. And somewhere in that long transformation, the conditions for you arose. You are breathing the end product of one of the longest chemical reactions in the history of the planet. The air itself is an inheritance, ancient, reworked, still arriving. Beneath Yellowstone, the heat does not stay still. It wanders. The geysers and hot springs of Yellowstone are not fixed features. They change. New ones appear. Old ones quiet down. The precise locations of thermal activity shift over years and decades as the hydrothermal system beneath, driven by the vast heat of the magma below, finds new pathways through the rock, opens new fractures, closes others that have become sealed by mineral deposition. Old Faithful, the most famous of the geysers, is faithful in the sense that it erupts regularly, but even its interval has changed over decades, lengthening slightly after earthquakes that altered the plumbing beneath it. The geyser is not a machine. It is a living system, responsive, sensitive to changes deep in the rock below it, in ways that no one fully predicted and no model entirely captures. Scientists who study Yellowstone's hydrothermal system speak of it with a kind of affectionate uncertainty. They know a great deal. They have mapped the temperatures, the pressures, the flow rates of water through different sections of the system, and they know that the system surprises them, that a new thermal feature appears, or an old pool changes color, or a previously quiet patch of ground begins to warm, and they add the observation to their records and adjust their understanding slightly and continue watching. Picture a researcher kneeling beside a hot spring at Yellowstone in the early morning, the steam rising, the water a vivid blue, the surrounding boardwalk slick with condensation, writing in a notebook while somewhere far below, the Earth continues its slow conversation with itself. The planet does not hold still for our maps. It simply continues, and we continue learning its language. Diamonds rise to the surface on the slowest elevators the Earth has ever made. They form in the mantle not near the surface, not even in the upper mantle, but deep within it, where the pressure is so immense that carbon atoms are forced into the rigid, interlocking structure that makes them the hardest natural substance on Earth. At those depths, they are simply part of the rock, unremarkable, in the way that extraordinary things are unremarkable when they are in their proper place, and no one is yet there to notice them. What brings them up is a volcanic process. Certain rare eruptions, kimberlite eruptions, originate from those extraordinary depths and move upward with unusual speed. They carry with them fragments of the mantle, including whatever diamonds happen to be present, and they deliver them to the surface in pipe-shaped intrusions of rock called kimberlite pipes. The eruptions themselves are ancient. Most of the world's diamond-bearing kimberlites were emplaced hundreds of millions of years ago. The diamonds inside them are older still. Some of the diamonds found in kimberlite pipes are more than 3 billion years old, formed in a mantle that looked nothing like the one beneath your feet today. In a world without complex life, without oceans in their current configuration, without continents arranged in any shape that would be recognizable on a map, they rose from that ancient depth on an eruption that has long since cooled and quieted, and they have been sitting in the rock ever since, waiting. 3 billion years of patience, delivered upward by volcanic fire, found finally by someone with a light. Some volcanic lakes are so calm, they hold two skies. On a still morning, with no wind and the air barely moving, a crater lake becomes a mirror, not a partial mirror, a complete one. The reflection so precise, so unbroken, that the boundary between the water and the sky becomes invisible, and the whole scene appears to be a vertical slice through a world where everything exists twice. The clouds above are the clouds below. The blue of the sky is the blue of the water. The rim of the volcano, reflected, completes itself beneath the surface. There are crater lakes in Rwanda, in the region around the Virunga Mountains, a landscape of old volcanoes, forested slopes, morning mist, where this effect happens regularly. Locals in the region have lived beside these lakes for generations, have named them, have fished them in small boats that cut the surface and briefly dissolve the reflection before it reforms behind them. The stillness of these lakes is not merely aesthetic. It is also a scientific signal. A crater lake that is perfectly calm and shows no bubbling, no discoloration, no surface temperature. Anomalies is a crater lake where the volcanic system below is quiet, where the heat is low and the gases are minimal. The stillness is the lake's own measure of the peace beneath it, a mirror and a monitor, beauty and information, held in the same surface. Even as you rest right now, somewhere a crater lake is reflecting a night sky it will hold until dawn changes the light. The stars above it and the stars below it are, for now, the same stars. The magma beneath a volcano moves with a patience that makes glaciers seem hurried. Magma, partially molten rock, studded with mineral crystals, charged with dissolved gases, is not what most people picture when they imagine something molten. It is not free-flowing, not liquid in the way water is liquid. In many magma systems, it behaves more like cold honey left in a jar on a winter morning. It moves, but slowly, under pressure, and only because the conditions demand it. The magma chamber beneath a large volcano can take tens of thousands of years to accumulate enough material and pressure to drive an eruption. Tens of thousands of years of slow addition fresh magma rising from the mantle below, intruding gradually into the chamber, warming the existing rock, dissolving gases, building pressure so incrementally that no single year would register as different from the last. And then, eventually, the conditions tip. The pressure exceeds what the overlying rock can hold, and what has been building, quietly, for 10,000 years or 50,000 years, begins to move. Picture that timescale laid against a human life. A magma chamber that began filling when the first human beings were painting animals on cave walls in southern France is still filling now. Still patient, still nowhere near its threshold, still doing what it does, which is wait and accumulate and hold. We measure our lives in decades. The Earth measures its processes in epochs, and somewhere between those two timescales, on a planet patient enough to hold both, we exist. There are instruments in the world right now that can feel the Earth's own pulse. Seismometers, the instruments that detect ground motion, have become so sensitive in recent decades that they register not only earthquakes and eruptions, but the subtler, continuous vibrations of the Earth itself. The ocean waves beating against coastlines produce a low, constant hum in the ground that seismometers detect everywhere on the planet, all the time. Scientists call it the Earth's hum, and volcanic tremor the distinct, rhythmic vibration produced by magma moving through rock rides within that hum, identifiable to those who know what to listen for. At volcano observatories around the world, scientists watch these signals the way a doctor watches a patient's vital signs, not looking for crisis necessarily, but maintaining the ongoing relationship of attention that allows crisis to be recognized early if it comes. The signals scroll across screens in real time. They are recorded and archived. They are compared to signals from previous episodes of unrest. They are discussed in weekly meetings and monthly reports, and papers published for others who study the same mountains on the other side of the world. The scientists who do this work describe a particular quality of attention that develops over years of watching the same volcano, a kind of intuition that is not mystical but deeply empirical, a sense for what the instrument is saying that goes beyond reading numbers. The volcano becomes known, its particular rhythms become familiar, its variations from baseline become recognizable. People who listen carefully enough to one thing begin to understand it in ways that go beyond description. The Earth has been making its sounds for 4.5 billion years. We have been listening for a very short time, and already we are beginning to hear something. Once, the sun went quiet for years, and in the cold and the dark, something shifted between people. In 1815, the eruption of Mount Tambora in Indonesia released more material into the atmosphere than any eruption in recorded human history. The ash and sulfur dioxide reached the stratosphere and spread, carried by high-altitude winds, across the entire planet. The following year, 1816, became known in parts of Europe and North America as the year without a summer. Temperatures dropped. Frosts came in June. Crops failed. The sky in the evenings turned strange colors, pinks and purples and deep oranges, beautiful and wrong. The light filtered through a veil of volcanic particles, suspended miles above the ground. And in that cold and disrupted year, people gathered. They stayed indoors. They told stories. A group of writers and poets sheltering in a villa on Lake Geneva during what should have been a warm summer began telling each other ghost stories to pass the grey, unseasonal evenings. One of them, a young woman named Mary Shelley, began telling a story about a scientist and the thing he made. That story became Frankenstein. The volcanic winter did not cause the story, but it made the room. It brought the cold through the windows and the strange light through the clouds, and the particular quality of an evening that goes on longer than it should, because no one wants to step outside into a summer that has forgotten how to be warm. Some of the most enduring things humans have made were made in the shelter the world's disruptions created for them. The volcano did not mean to make a room, but the room was made. The blood in your veins carries the memory of a dead star and a very old mountain. Iron, as an element, is forged only under conditions of extreme stellar gravity in the cores of massive stars, in the final stages of their lives, when the fusion reactions that have sustained them for billions of years finally reach the end of what they can produce. Iron is, in a sense, the ash of stellar burning, and when those stars collapse and explode, they scatter that iron into space. It arrived on early Earth as part of the planetary material that accumulated under gravity. The planet concentrated its iron sinking toward the core, but some remaining in the mantle, cycling upward through volcanic processes into the crust, into the rock, into the soil, from soil into plants, from plants into the animals that ate them, from those animals, eventually, into you. The iron in your hemoglobin, the iron that allows your blood to carry oxygen from your lungs to every cell in your body, the iron that is, in a very real sense, what keeps you alive right now, was made in a star, distributed by an explosion, carried by gravity into a young planet, cycled upward by volcanic heat, absorbed by life, passed through uncountable bodies over hundreds of millions of years before it arrived in yours. Even as you rest right now, that stellar iron is moving through you with every heartbeat, doing its ancient work, carrying the oxygen that keeps the thought alive, the breath continuing, the sleep deepening. You are not made of ordinary material. You are made of what stars leave behind. A mountain can be buried so completely by life that it forgets for a while what it is. On the slopes of old volcanic mountains, mountains that have been dormant long enough for soil to develop, for rainfall to establish itself in reliable patterns, for seeds to arrive by wind and bird and current, forests grow that seem to have no memory of fire. The canopy closes overhead. The understory fills with ferns and mosses, and the particular shade-loving plants that thrive in the filtered light beneath tall trees. The ground is soft with accumulated organic matter. Water moves through it slowly, held by roots. Walking through such a forest, on the slopes of an old volcano in Hawaii or Costa Rica or the Pacific Northwest, you would not think this ground was once flowing rock. You would think, this is as old as forests get. This is what a forest looks like when it has had time to become fully itself. And yet the volcanic origin is present in everything. In the mineral richness of the soil that makes the trees grow tall. In the particular drainage patterns shaped by ancient lava, flows beneath the surface. In the chemistry of the groundwater that feeds the roots. The forest is not separate from the volcanic history. It is the volcanic history, transformed, turned, slowly, by rain and biology and time, into something green and breathing and alive. The mountain did not forget. It became what we think of as nature wild, untouched, primordially green, is often the volcano's longest and most patient project. Fire becoming forest, destruction becoming shelter, the mountain continuing its work in a different register. The youngest ground on Earth has never been touched by wind or rain, or any living thing, and it exists right now. On the southeastern coast of the big island of Hawaii, active lava flows from Kilauea, periodically reach the ocean, and extend the island's coastline into the sea. The rock that forms there cooled within minutes of leaving the volcanic vent, hardened almost instantly by the cold salt water, is, in the most literal geological sense, brand new. It did not exist last year. In some cases, it did not exist last week. It is the newest surface on the planet, created in real time, extending the landmass of Earth by a small, incremental amount that will be measured and recorded by scientists who monitor the island's growth. That new rock is black and rough, and still faintly warm to the touch, if you could stand near it, though the shoreline where it forms is often turbulent, surrounded by the steam and lays of lava meeting water. It is not yet a surface for anything. No lichen has landed on it. No rain has dissolved its minerals. No root has found a crack. It is simply rock elemental, unmediated, straight from the mantle. Somewhere between 10 and 50,000 years from now, that same rock will be soil. Life will have found it, colonized it, died on it, and in dying, enriched it. Rain will have worked its minerals loose. Wind will have carried seeds to it. And what is now bare black stone will be, in that distant future, a piece of ground that someone might stand on and call beautiful, without knowing anything about how recently it arrived. The Earth is still arriving, quietly, at the edge of the water, in the place where land is being made. Even tonight, the island is a little larger than it was yesterday. Deep beneath the ocean, there are geysers that have never seen light, and they are surrounded by life. Hydrothermal vents on the sea floor, discovered only in 1977, which means they were unknown to science for the entirety of human history, until very recently, produce plumes of superheated, mineral-rich water that emerge from the seafloor at temperatures that would be lethal to most life. Around them, in the cold and the absolute darkness, entire ecosystems thrive. Not ecosystems that depend, even distantly, on sunlight. Not ecosystems connected to the surface food web by any thread. These are communities of organisms, tube worms as long as your arm, ghostly pale crabs, shrimp without functional eyes, bacteria living in the vent chimneys themselves that run entirely on chemical energy. On the reactions between the hot mineral-laden vent water and the cold seawater, on a process called chemosynthesis, which is photosynthesis's dark twin life, made from chemistry rather than light. The tube worms, in particular, have become a kind of emblem of this discovery. They have no mouths, no digestive systems in the conventional sense. They host, inside their bodies, bacteria that perform chemosynthesis and share the energy with their host. The worm and the bacteria live as one organism, sustained by the chemistry of the vent. in the dark, at the bottom of the ocean. We once thought sunlight was the non-negotiable foundation of all life. We were wrong. Life is more resourceful than our definitions of it. Somewhere in the deep Pacific right now, in a darkness no light has ever touched, something is living on heat alone. Snowfall inside a volcanic crater is one of the quietest contradictions the Earth produces. Some volcanoes are tall enough and located at latitudes where winter arrives with genuine cold that their upper reaches collect snow. The crater, that depression at the summit, the very mouth of the volcano, fills with white ice forms along the inner walls. The same structure that, in an active phase, channels fire and gas upward becomes, in winter dormancy, a bowl of snow resting on a mountain that holds warmth below. Mount Fuji, the great stratovolcano of Japan, carries snow on its upper cone for most of the year. The crater at its summit fills with it in winter and holds it well into spring. Pilgrims and hikers who reach the rim in early season sometimes find themselves looking down into a white bowl, the snowfield curved and still. The crater walls rising around it fire's architecture, filled with winter's water. Etna, in Sicily, has been known to erupt and simultaneously hold snow on its upper slopes. The heat of the eruption melting channels through the snowfield, fire and ice negotiating the same terrain at the same moment. This is not a contradiction the mountain finds remarkable. It is simply what it is, a thing large enough to hold opposites without needing to resolve them. Cold and warm, ancient and new, sleeping and alive. The volcano, in its dormancy, holds all of these at once. Some things are large enough to contain their own contradictions. They do not choose between what they are. They simply hold it all. Everywhere across the Pacific, the stones people walked on to cross the ocean were made by volcanoes. The Pacific is the largest geographic feature on Earth, covering more area than all the continents combined, stretching from pole to pole, wider at the equator than the moon is from the Earth. And yet people crossed it. The Polynesian navigators, among the greatest maritime explorers in human history, crossed it in outrigger canoes, using the stars and the waves and the flight patterns of birds to find their way from island to island to island, across an ocean with no landmarks. Those islands were made by volcanoes. Every island in the Pacific, every stepping stone, every place of landfall, every garden and harbor and burial ground rose from the seafloor on volcanic heat. The hotspot chains, the arc island chains, the isolated seamounts that barely break the surface, all of them products of the same inner fire, distributed across the world's largest ocean by the movement of tectonic plates. Without volcanic activity, the Pacific would be unbroken water from one side to the other. The navigators would have had nowhere to go. The cultures that developed on those islands, the languages, the traditions, the navigational knowledge itself would not exist. The birds that guided navigators to land would have had no land to nest on. The whole human story of the Pacific was made possible by heat rising from the mantle. Even the greatest human journeys have always been, in some sense, journeys from one piece of volcanic rock to another. The Earth made the path. People found the courage to walk it. Scientists have learned to feel what they cannot see, and what they feel is the Earth's own heartbeat. The instruments at volcano observatories around the world do not only listen, they tilt. GPS receivers mounted on volcanic slopes measure the ground's position to within millimeters, tracking the inflation and deflation of the volcano as magma moves below, the way a doctor might track the rise and fall of a chest. When magma enters a chamber, the ground above it swells. When magma drains or cools and contracts, the ground subsides. These movements are tiny centimeters over months, sometimes millimeters, but they are real, and they are measurable, and they tell a story. At Kilauea, decades of GPS data have produced a portrait of a volcano breathing, inflating before eruptions, deflating during them, slowly refilling afterward as the magma system replenishes itself from below. Scientists who have watched this data over careers can see the volcanic cycle, the way a musician can hear a familiar piece not note by note, but as a whole, as a shape, as something with rhythm and direction. There is something deeply human about this kind of attention. The patient, decade-long watching of a single mountain, the willingness to sit with uncertainty, to record what you see, to build understanding slowly rather than rushing toward conclusions. The scientists who do this work are not waiting for disaster. They are simply in relationship with something large and old and alive. The Earth breathes in ways that take years to complete a single breath. And there are people who have dedicated their lives to watching it breathe. Attention, given long enough to one thing, becomes a form of love. There is a fire in the Earth that has been watched by human eyes longer than almost anything else. Kilauea's lava lake, that slow, glowing pool of molten rock sitting in the crater at the Volcanoes summit, has been observed by people for as long as people have lived on the big island of Hawaii. Ancient Hawaiians watched it. They named it. They understood its changes as communications from Pele, as moods, as signs to be read carefully by those who knew how. The glow visible at night from the crater rim red and amber and slow, pulsing gently with the movement of the lava surface below, is one of the oldest continuously observed natural phenomena on Earth. Early Western visitors to Hawaii in the 19th century described descending to the crater rim at night and standing at the edge, looking down into the glow, feeling the heat rising against their faces in the cool night air. They wrote about it with the particular breathlessness of people encountering something. They had no framework for something that was not dangerous in the immediate sense, but that bypassed all rational assessment and went directly to Brudo, something older, something that recognized fire the way the body recognizes warmth. The lava lake is not constant. It rises and falls. It drains and refills. There have been decades when it was absent, and the crater was cold and dark. And then it returns slowly, quietly, and the glow comes back, and people come again to stand at the rim in the night and look down at it. A fire that has been watched for 1,000 years is no longer simply a geological feature. It is a meeting place, a place where the planet and its people have been keeping the same appointment, in the dark, across generations. The gas that rises through volcanic rock and into the atmosphere carries, sometimes, the seeds of rain. Volcanic eruptions release sulfur dioxide into the atmosphere, and sulfur dioxide, once in the upper air, undergoes chemical reactions with water vapor and oxygen to form tiny sulfate particles. These particles are aerosols so small they are invisible individually, but collectively capable of doing something remarkable. They become cloud condensation nuclei, the tiny centers around which water vapor can condense to form droplets, the starting point of a cloud. This means that volcanic eruptions, beyond all their other effects, can seed clouds, can contribute to rainfall patterns, can alter, in some small measure, the distribution of precipitation across a region. The volcano exhales, and weeks later, somewhere downwind, a cloud forms around a particle that began its journey in the Earth's own breath. The largest eruptions make this effect visible, and measurable stratospheric sulfate layers from major eruptions have been linked to rainfall anomalies in the years following. But even modest volcanic outgassing contributes, quietly and continuously, to the chemistry of the atmosphere and the behavior of clouds. Picture a cloud forming over an ocean white, slowly building. The kind of cloud that will eventually produce rain somewhere. And inside it, at the center of each water droplet, a particle so small it has no name in ordinary language. A particle that rose from the Earth's interior through a volcanic vent, traveled into the sky, and became the seed of something that will fall as rain on a forest that has never known the volcano that made it possible. The Earth's breath becomes the sky's water, and the water falls back to the Earth, carrying the memory of its origin in its chemistry. Everything returns. Everything is always in the middle of returning. Where lava meets salt water, land is not just made, it is announced. The coastline of a volcanic island in its active phase is not a quiet place. Where lava flows enter the sea, the ocean hisses and steams and the air fills with the white billowing cloud of lays, that fine, warm mist of steam and tiny glass particles that marks the boundary between the newest land on Earth and the oldest ocean. The sound is continuous, a deep, sustained hiss underlaid by the crackle of cooling rock and the rhythmic percussion of waves meeting a shore that is actively, visibly changing. And at night, in that same place, something extraordinary becomes visible. The lava glows. Not the dramatic, rushing orange of a lava fall, but a deep, steady red visible through the cracks in the cooling surface rock, through the thin places where the hardened skin is not yet thick enough to fully contain the heat below. The shoreline pulses faintly. New ground lit from within, cooling slowly, going from red to black as each section solidifies. People who have stood at that shoreline at a safe distance, in the dark, watching the lava enter the ocean, describe the experience as one of the most profound of their lives. Not exciting in an adrenaline sense, profound in the older sense of the word, deep, moving towards something beneath ordinary feeling. They are watching the earth make itself, in real time, at the edge of the water, in the dark. There are not many places in the world where creation is visible to the naked eye. This is one of them, and it asks nothing of the watcher except to stand still and pay attention. Beneath every continent, the slow churning of rock keeps the surface from ever going entirely still. The mantle, that vast layer of rock between the Earth's crust and its core, is solid in the sense that it is rock. But over the timescales of geology, it behaves like a fluid. It convects. Hot material near the core rises slowly, over millions of years, toward the surface. Cooler material near the base of the crust sinks. The whole system turns in enormous, slow loops, like the circulation of a pot of water heating on a stove, except the pot is the size of a planet, and the heating takes billions of years. This convection is what drives plate tectonics. It is the engine beneath the engine, the reason the plates move, the reason volcanoes exist, where they exist, the reason the continents are arranged as they are and will be arranged differently in 100 million years. The whole dynamic history of the Earth's surface, every mountain range, every ocean basin, every volcanic island chain, is ultimately a product of rock circulating in slow loops, driven by heat. The mantle beneath your feet right now is moving, not in any way you could feel, not in any way that would register in a human lifetime, or 10 human lifetimes, but moving, turning over, slowly, in the dark below the crust, carrying heat upward and sending cooled rock back down. The ground feels permanent because we are too brief to feel it move. But permanence and stillness are not the same thing. The most permanent things in the world are also, always, slowly, in motion. A city in northern Europe stays warm all winter on the heat of a mountain it has never seen erupt. Reykjavik, the capital of Iceland, sits on a volcanic island above one of the most geothermally active regions on Earth. Beneath the city, hot water circulates through volcanic rock, heated by the same magma systems that drive Iceland's frequent eruptions elsewhere on the island. And that hot water is piped quite directly, quite practically, into the radiators of Reykjavik's buildings, the hot water taps of its kitchens, the geothermal pools, where residents swim outdoors in winter steam. Nearly all of the city's heating comes from this volcanic source, not from burning fuel, not from generating electricity and converting it to heat, from water that is already hot, heated by the earth, pumped from the ground, and circulated through the city and returned. A system so simple and so elegant, it is difficult to believe it took until the 20th century to implement fully. The result is a city that smells faintly of sulfur from its hot water, a reminder, mild and present, of what is keeping it warm. Children who grow up in Reykjavik grow up knowing that the warmth in their homes comes from the ground, that the earth is heating them, that the volcano, far away and mostly quiet, is tending them in its own ancient way. There is something quietly profound about a city warmed by a planet that does not know it is warming anyone. The Earth does not give with intention. It simply gives continuously, generously, from an inner fire that has never gone out. And we have learned, in some places, to receive that gift with gratitude and good pipes. The eruption that covered Pompeii preserved an ordinary afternoon for 2,000 years. On the morning of August 24th in the year 79, the people of Pompeii were doing ordinary things. Bread was in the ovens. Wine was in the jugs. Merchants were at their stalls. Children were playing in the streets. Dogs slept in the sun. It was, by all evidence, a morning that expected to become an afternoon, and then an evening, a morning with no particular awareness of its own significance. And then Vesuvius, which had not erupted in living memory, which had been growing wine grapes on its fertile slopes, which had been trusted the way all familiar things are trusted, erupted. What followed over the next hours was catastrophic. But what followed over the next 2,000 years was something almost impossible: preservation. The ash and pyroclastic material that buried the city also sealed it, protected it from the decay that time usually brings. When excavations began in the 18th century and continued into our own time, they found not ruins in the ordinary sense, but moments, frozen moments. The bread, carbonized but still in the oven's shape. The cart ruts worn into the paving stones by 1,000 ordinary mornings of traffic. The graffiti on the walls, jokes, declarations of love, political endorsements, drawings exactly as they were left. And the spaces left by bodies, voids in the ash where people had been filled carefully with plaster by excavators, producing forms that are heartbreaking in their specificity. A person curled on their side, a dog still chained. The volcano did not mean to preserve them. It simply covered them, and the covering became a kind of impossible gift to the future. We know more about an ordinary Roman morning than about many events that happened centuries later. The Earth, sometimes, keeps things we did not know we would want to remember. Some volcanic gases, rising through cold groundwater, make it fizz. Carbon dioxide is one of the primary gases released by volcanic systems, not just during eruptions, but continuously, from the slow outgassing of magma chambers and hydrothermal systems. In some volcanic regions, this carbon dioxide rises through groundwater, dissolving into it under pressure, producing water that is naturally carbonated, sparkling, fizzing gently with bubbles that have no human origin. There are springs in Germany, in the Eifel volcanic region, that have been producing naturally carbonated water for as long as recorded human history. The Romans knew them. They built around them. The word we use for a type of sparkling water, selters, seltzer, then seltzer, comes from the name of one of these towns, Selters, where a volcanic spring produced water that people valued enough to bottle and trade across the ancient world. The carbon dioxide in those bubbles rose from a volcanic system that has been quietly outgassing for tens of thousands of years. It dissolved into groundwater moving slowly through volcanic rock. It arrived at the surface in a spring, still dissolved, releasing its bubbles gently when the pressure dropped as the water emerged into open air. Someone, long ago, tasted it, found it pleasant, remarkable, somehow refreshing in a way that still water was not. And so the Earth's volcanic breath became a beverage, one of the oldest and most widely consumed in the world. Even tonight, somewhere, someone is drinking the exhalation of a volcano and finding it good. The oldest ocean crust is always, already, on its way home. Ocean crust forms at the mid-ocean ridges, pulled apart by the spreading of plates, filled by upwelling magma, solidified and carried outward on the slow conveyor of plate tectonics. The oldest ocean crust, by the time it has traveled from ridge to trench, is around 200 million years old. Young, in geological terms. Young enough that the dinosaurs were still in their early chapters when it formed. At the subduction zones, those long trenches at the edges of ocean basins, where one plate dives beneath another, this crust returns to the mantle. It descends slowly, over millions of years, sinking into the heat below. As it does, it releases water and carbon dioxide back into the mantle and into the overlying crust, triggering melting, feeding the volcanoes that line the subduction zone above. The old seafloor becomes new magma. The new magma becomes new volcanic rock. The new volcanic rock eventually erodes and returns to the ocean as sediment. The whole cycle from ridge to seafloor to trench to mantle to volcano to surface takes on the order of 200 million years to complete, a loop so large it barely fits inside the mind. And yet, it is running continuously, at every scale, all the time. The Earth does not make things and then abandon them. It cycles them, returns them, transforms them, and sends them around again. Nothing is wasted. Nothing is truly gone. Everything the planet has ever made is still here, in one form or another, being made again. The ground beneath a caldera does not fall in a moment. It takes its time. When the magma that supports the roof of a volcanic chamber begins to withdraw, drained by eruption, or simply sinking back into the deeper earth the rock above it loses, gradually, the pressure that was holding it up, and it begins to settle, not all at once, not dramatically. In stages, over hours or days or sometimes weeks, the surface lowers itself by increments, each small movement releasing a little more of the tension that had been building in the overlying rock. Scientists who have monitored caldera collapses in real time describe them as unexpectedly graceful events. The ground does not crack and plunge, it steps down, in discrete intervals, like a slow staircase descending into the earth, each step accompanied by a small seismic signal and a measurable drop in the GPS elevation of the monitoring stations on the surface above. At Kilauea in 2018, a caldera collapse was observed in extraordinary detail, the most thoroughly instrumented such event in history. Over weeks, the floor of the summit crater dropped by hundreds of meters, in thousands of small steps, each one recorded. Scientists watching the data in real time could see the pattern almost immediately. The collapse had a rhythm, a cadence, small drops, then a pause, then another small drop, like something finding its way down a staircase in the dark, carefully, one step at a time. The Earth, even in its most dramatic reconfigurations, tends toward the gradual. It has all the time it needs. It has never been in a hurry, and the patience with which it rearranges itself is one of the quietest and most consistent things about it. Ancient Rome walked on volcanic stone, and that stone is still holding. The Romans built their roads using a material called basalt volcanic rock, quarried from the flows around the volcanic fields of central Italy, cut into irregular polygonal blocks, and fitted together with extraordinary precision on a carefully prepared roadbed of gravel and sand. The basalt was chosen deliberately. It was hard. It resisted wear. It did not become slick in rain the way smoother stone might, and it could be laid in interlocking patterns that distributed weight across the whole surface, rather than concentrating it at any single point. Some of those roads still exist, not as museum pieces behind glass, but as actual surfaces still in use, or still intact, in Rome and in the towns along the old consular routes. The Appian Way, the most famous of the Roman roads, still has sections of original basalt paving that have been walked on, driven over, rained on, and sunned for 2,000 years. The blocks have worn smooth with use, but they have not crumbled. They have not separated. They are still there, holding their pattern, doing what they were laid to do. The volcanic rock that built them was already ancient when the Romans quarried it, formed in eruptions hundreds of thousands of years earlier, cooled and hardened over geological time, then cut and shaped by human hands, and placed in the service of an empire that no longer exists. The empire is gone. The road remains. Volcanic rock outlasts almost everything that is built upon it, and in outlasting, it carries the memory of the people who shaped it. Stone remembers what it has held. It simply does not speak about it unless you know how to listen. The carbon that once warmed ancient worlds now sleeps inside the ground you walk on. Carbon dioxide, released by ancient volcanoes, entered an early atmosphere and warmed the planet, a natural greenhouse effect that, in the deep past, prevented the Earth from freezing entirely during periods when the sun was fainter than it is today. Life absorbed that carbon photosynthetic organisms, drawing it from the air, building their bodies from it, dying and sinking to the seafloor where they accumulated in layers of organic material under pressure. Over millions of years, that organic material transformed. Under heat and pressure, the carbon-rich remains of ancient marine life became oil, became natural gas, became coal, the compressed remains of ancient forests that grew in swampy lowlands during periods when volcanic carbon dioxide had enriched the atmosphere enough to drive extraordinary plant growth. The carbon that volcanoes released into the sky 300 million years ago is the same carbon that was absorbed by those forests, that became coal, that was burned, beginning in the Industrial Revolution, and is now, again, in the atmosphere, completing a cycle so long that no human civilization existed at its beginning. The Earth has always cycled its carbon, releasing it, capturing it, releasing it again. What has changed is the speed. The natural volcanic cycle operates over millions of years. What we have done operates over centuries. The carbon in the coal was a volcanic gift, held in trust by the Earth for hundreds of millions of years. We have been drawing on that trust very quickly, and the Earth, patient as it is simply recording the change. There is a flame burning in Indonesia that has no color that fire usually has. On the slopes of Ijen volcano in East Java, in the hours before dawn, a phenomenon occurs that looks less like something geological and more like something from a dream. Sulfuric gases, emerging from the volcanic vents near the crater lake, ignite when they meet the oxygen of the night air. But sulfur does not burn orange or yellow, it burns blue. A vivid, electric, otherworldly blue flames that reach meters high in some places, flowing downhill along channels in the rock, like a river of cold blue light. The blue fire of Ijen has been described by everyone who has seen it as profoundly disorienting in the best possible way. The eye expects fire to be warm in color. It is one of the most deeply held visual associations humans carry, formed around campfires for hundreds of thousands of years. And then the Ijen flame arrives and contradicts everything that expectation holds, quietly, without violence. In the blue pre-dawn of an Indonesian mountainside, sulfur miners work near these vents at night, collecting solid sulfur that has crystallized around the vent openings, carrying it in baskets down the mountain in the dark. They move through the blue light the way workers move through any light purposefully, practically, their breath masked against the gases. The extraordinary, for them, has become the ordinary context of labor. Blue fire, carried baskets, a crater lake glowing faintly at the bottom of the dark. The Earth does not reserve its most unusual things for special occasions. It simply produces them, quietly, in the hours before the rest of the world is awake. A volcano can leave its mark on the sky for years after it has gone quiet. When a large eruption sends material into the stratosphere above the weather, above the rain that would otherwise wash it out, the tiny sulfate particles that form there can remain suspended for 2 to 3 years, carried by stratospheric winds around the planet, distributed evenly at altitude. They scatter incoming sunlight in particular ways. The effect on sunsets is one of the most quietly beautiful consequences of a major eruption. The additional particles in the upper atmosphere scatter light at wavelengths that produce colors. The sky does not ordinarily reach deeper pinks, more saturated purples, oranges that seem almost architectural in their richness. Artists in the years following large eruptions have left records of these skies in their paintings without knowing what made them. Art historians, Studying the colors of sunsets in works from the months after Krakatau or Tambora can sometimes identify the volcanic influence in the palette. Turner's famously vivid sunset paintings from the early 19th century works, whose colors were considered by some contemporaries to be exaggerated, too saturated to be real, were painted during a period when volcanic aerosols from multiple eruptions were still present in the stratosphere. Turner was not exaggerating. He was simply painting what he saw. The sky was telling the truth. The painters who trusted their eyes were the accurate ones. Even as you rest right now, the atmosphere above you holds trace particles from eruptions that happened years ago, mixing with the ordinary air, scattering light in ways too subtle to notice. Every sunset you have ever loved has been, in some small measure, made by the Earth's own exhalations. The silence inside a lava tube is older than any building on Earth. When you descend into a lava tube through a collapse opening in the ceiling, down a carefully placed ladder into the dark below, the first thing that changes is the sound, or rather, the sound leaves. The ambient noise of the surface world wind, bird song, distant traffic, the thousand small audio textures of an inhabited landscape, simply stops. What remains is something that is not quite silence, but is as close to it as the terrestrial world offers. The tube itself produces no sound. The rock walls, cooled and stable, do not creak or settle. There is no water dripping. In most dry tubes, no wind. The air moves only in the most imperceptible way, pulled by the slight temperature difference between the interior and the surface. And the temperature itself is constant, the same year-round, buffered by the insulating rock above from all the seasonal variation of the surface world. Lava tubes on the big island of Hawaii have been used by ancient Hawaiians for shelter, for burial, for ceremony places where the rock held a particular quality of stillness that marked them as significant. The silence in those tubes is the same silence those people stood in, unchanged by what has happened on the surface above them, indifferent to the centuries. There are lava tubes in Iceland long enough to walk through for kilometers, dark tunnels through the basalt, their floors sometimes icy, where cold air pools in winter and freezes any moisture. And in those icy sections, the silence has a texture, a coldness that somehow makes it more present, more felt. The earth made these rooms and then went quiet inside them, and the quiet has been kept ever since. The sky above a volcanic eruption makes its own weather. Large eruptions produce convective columns of ash and gas that rise so rapidly and so high that they generate their own atmospheric dynamics. The column carries enormous heat into the upper atmosphere, and that heat drives powerful updrafts, and those updrafts interact with the moisture in the air to produce clouds, not the gentle cumulus clouds of a summer afternoon, but dense, rapidly forming cumulonimbus that can top out at the height of commercial aircraft. And inside those clouds, lightning. Not the ordinary lightning of a thunderstorm, which requires the slow charge building of convection and ice crystals over an hour or more. Volcanic lightning forms within minutes, sometimes within the eruption column itself, before it has even formed a proper cloud. The mechanism involves ash particles colliding and exchanging electrical charges at extraordinary speeds, generating voltage differences that discharge as lightning in colors that range from the ordinary blue-white to a deep orange-red that reflects the glow of the eruption below. Photographs of volcanic lightning, the dark eruption column lit from within by branching bolts, the sky around it lit by the reflected glow of the lava, are among the most visually extraordinary images that natural phenomena produce. They look, genuinely, like something from mythology, like the sky responding to the ground. In a sense, it is. The ground is sending heat upward. The sky is returning electricity downward. A conversation between the earth and the atmosphere, conducted in fire and light. The volcano does not simply erupt into the sky, it changes the sky. Briefly, dramatically, the mountain and the weather above it become one system, inseparable, interdependent, speaking the same language. Scientists can read 200,000 years of time in a stone, and the stone does not even know it is a record. When volcanic material is erupted, it often contains minerals that include trace amounts of radioactive elements, uranium, potassium, argon, whose decay rates are known with extraordinary precision. These elements decay at rates so consistent, so independent of temperature and pressure and chemistry, that they function as clocks. From the moment the rock solidifies and the radioactive decay clock begins, the ratio of parent element to daughter element records the time elapsed as precisely as any instrument humans have made. This is radiometric dating, the method by which geologists determine the ages of volcanic rocks, and through volcanic rocks, the ages of the events associated with them. A lava flow from 200,000 years ago can be dated to within a few thousand years. An ash layer preserved in sediment can be matched to a specific eruption and given a specific date. The timeline of Earth's volcanic history, which is also, in many ways, the timeline of Earth's geological history, has been built from these measurements, one dated sample at a time. Picture a geologist in a laboratory, working with a small piece of volcanic rock collected from a remote outcrop. The rock is ordinary looking, grey, dense, unremarkable, and inside it, the ratio of isotopes tells a story the rock was not aware it was telling, the story of when it cooled, when the clock started, how long it has been traveling through time since that moment. The Earth keeps records it does not know it is keeping, and we have learned, slowly, to read them. Every volcanic rock is an archive. Every sample collected is a sentence recovered from a very long book. The deepest quiet on land belongs to a place that was made by fire. Spelunkers and scientists who have spent time in the most remote lava tubes, those far from any entrance, buffered by hundreds of meters of solid basalt in every direction, describe a quality of stillness that has no equivalent in ordinary life. It is not the quiet of a library, or a forest at dawn, or a room at 3 in the morning. Those silences still carry the possibility of sound. They are absences in a world that normally produces noise. The silence inside a deep lava tube is different in kind. It is a silence that has never been otherwise, a silence that predates the existence of anything that makes sound. The tube formed in darkness and has remained in darkness, and has been silent since the last of the lava drained away, perhaps 10,000 years ago, perhaps 50,000. Nothing has happened inside it since then. Nothing at all. Scientists studying these spaces sometimes sit, deliberately, in that silence for extended periods, not meditating, not performing, but simply trying to understand what the absence of all sound does to human perception. What they report is consistent and somewhat surprising. After the initial adjustment, after the ears stop waiting for sound and accept that none is coming, what remains is not emptiness, but a kind of fullness, an unusual presence. The body, freed from the constant low-level task of processing ambient sound, becomes aware of its own interior, the heartbeat, the breath, the faint sound of blood moving. In the deepest quiet the earth can offer, what you hear is yourself. And that, somehow, is not lonely. It is clarifying. It is a reminder that you are here, and warm, and alive inside a planet that made a room and left it for you to find. A shield volcano grows so slowly it looks, from a distance, like it was always there. The word volcano, for most people, conjures a cone, a steep, symmetrical peak, rising to a dramatic point against the sky, the shape of Fuji, of Mayon, of the volcanoes drawn by children with a confident triangle and a zigzag of orange at the top. But the most common type of volcano on Earth, and in the solar system, does not look like that at all. A shield volcano is wide, enormously, almost implausibly wide relative to its height. Its slopes are so gradual, rising only a few degrees from horizontal, that standing on one, you would not know you were on a volcano. You would think you were walking across a gently tilted plain. The big island of Hawaii is essentially a shield volcano, or rather, several overlapping shield volcanoes, and its flanks extend into the ocean in every direction for hundreds of kilometers before finally dropping away to the sea floor. The shape comes from the lava. Shield volcanoes produce lava that is very low in silica and therefore very low in viscosity, thin and free-flowing, spreading outward rather than building upward. Each eruption adds a thin layer to an already thin structure, spreading it wider rather than taller. Over hundreds of thousands of eruptions, over millions of years, this produces the characteristic profile broad, low, curved, like a warrior's shield, laid face down on the ground. From the air, a shield volcano looks like the Earth simply bulging upward a little, like the planet is taking a slow, gentle breath beneath the surface, like the ground is simply more alive there than elsewhere, which is, in every meaningful sense, exactly what it is. Beneath the surface of Europa, one of Jupiter's moons, an ocean may be kept warm by volcanic heat. Europa is covered entirely in ice, a smooth white shell that wraps the moon in a surface so reflective that it is one of the brightest objects in the solar system. Beneath that ice, current scientific understanding suggests, is a liquid ocean, a vast, global ocean of salt water, kept from freezing by the same tidal flexing that drives the volcanic activity on Io, the gravitational squeeze of Jupiter's enormous mass, generating heat in the moon's interior. That interior heat, rising through the rocky mantle of Europa, may reach the ocean floor in the form of hydrothermal vents, volcanic features not unlike those on Earth's own seafloor, releasing heat and minerals into water that has never been touched by sunlight. If that is so, and scientists emphasize, carefully and honestly, that it remains an open and genuinely exciting question, then Europa's ocean may have the two things that, on Earth, are sufficient to support life: liquid water and chemical energy from volcanic heat. The same combination that supports the tube worms and blind shrimp and chemosynthetic bacteria of Earth's hydrothermal vents. No one knows, and the not knowing is part of what makes this fact worth sitting with in the quiet of a late night. Somewhere in the outer solar system, beneath a shell of ice on a moon of the largest planet, there may be an ocean warmed by volcanic heat, and in that warm, dark water, something may be living. The universe is large enough that we cannot yet say it is not so, and that openness, that genuine, honest not knowing, is one of the most beautiful things science offers. When pumice rafts cross oceans, they carry passengers who never chose to travel. After the eruption of Hunga Tonga in 2022, and after earlier eruptions in the Pacific and Indian Oceans, floating pumice fields formed on the ocean surface pale grey islands of volcanic glass, stretching for miles, bobbing in the swell, and on and within those floating fields, life gathered. Barnacles attached within days, bryozoans, small colonial organisms that filter water for food, colonized the porous surfaces. Small crabs found the rafts and rode them. Worms burrowed into the pumice's cavities. Scientists who study these rafts, sometimes called biological arcs, have found that they carry astonishing biodiversity. A single pumice raft, sampled carefully, can host hundreds of species. Species from the region where the eruption occurred, hitching a ride into ocean currents that will carry them, over months or years, to shorelines far from where they began. This process, called rafting dispersal, is thought to have been one of the primary mechanisms by which life colonized remote oceanic islands throughout geological history. Long before humans arrived at Hawaii or the Galapagos or any of the other isolated archipelagos of the Pacific, life had been arriving by pumice, riding the volcanic aftermath to new shores, finding, when the pumice finally beached or dissolved, that there was ground worth staying on. The volcano erupts, and its lightest debris becomes a vessel. The vessel gathers passengers. The ocean carries them. And life, which is extraordinarily good at going where conditions allow, arrives somewhere new. The eruption does not know it is sending ships. The organisms do not know they are sailing. And yet the journey happens, and the islands are richer for it. There is a place in the earth that is neither rock nor liquid, and it moves like neither. Below the lithosphere, the rigid outer shell of the earth that includes the crust and the uppermost mantle there, is a zone that geologists call the asthenosphere. It is solid, technically. The atoms are arranged in crystal structures as they are in solid rock. And yet, under the slow application of the enormous pressures and temperatures of its environment, it deforms. It flows. Not like water flows or lava flows, but like a substance with no good equivalent in ordinary experience, something between glass and tar and slow putty, yielding to stress over geological timescales, while remaining effectively rigid over the shorter timescales of earthquakes. The lithospheric plates, the tectonic plates that carry the continents and the ocean floors, float on the asthenosphere, the way pieces of ice float on water, except that the floating is imperceptibly slow, and the water is rock, and the ice is also rock, just slightly different rock, at slightly different conditions. In certain places, where the asthenosphere rises close to the surface at mid-ocean ridges, at volcanic hotspots, it partially melts. The pressure drops enough that some of the crystals in the rock give up their structure and become truly liquid. Magma forms, and that magma, lighter than the surrounding rock, begins its long, slow rise toward the surface. This is how every volcano begins, not in drama but in physics, in the quiet behavior of rock at the conditions it finds itself in. The Earth is always in negotiation with itself. Pressure against temperature, density against buoyancy, the rigid against the yielding. Volcanoes are simply where those negotiations reach the surface. The lava fields of Iceland have a color at night that exists nowhere else on Earth. Iceland sits on the mid-Atlantic ridge and above a mantle hotspot, making it one of the most volcanically productive places on Earth, relative to its size. Its landscapes are ancient and young, simultaneously ancient black basalt plains, smoothed and weathered over millions of years, alongside lava fields so recent they are still being colonized by the first mosses. And those moss-covered fields, the older ones, where time has softened the raw rock into something that can hold moisture and harbor. Life have a color in the particular quality of Icelandic light that is unlike any green you have seen elsewhere. Partly, it is the latitude. The light in Iceland arrives at an angle that southern landscapes rarely see, low, long traveling, warm in color, even when the temperature is cold. It falls across the moss, at a slant that makes each small plant visible individually, the whole field becoming a texture rather than a surface. And the green of the moss on the black basalt, the contrast between that vivid, almost luminescent green and the absolute darkness of the volcanic rock beneath, produces something the eye responds to before the mind has named it. In the long summer evenings, when the sun barely sets and the light hangs golden for hours near the horizon, those lava fields glow, not literally, but in the way that things glow when light finds them at exactly the right angle, and they respond by showing you what they are. Even as you rest right now, an Icelandic lava field is sitting in the long northern evening, covered in moss, that arrived 1,000 years ago and has been slowly, quietly, turning black rock green ever since. The volcano made the rock, the moss made the garden, and the light made it visible. The trees that grow on volcanic slopes remember eruptions their own roots did not experience. Dendrochronology, the reading of tree rings, records not only the age of a tree, but the conditions of every year of its life. Wide rings for good years, warm and wet and productive. Narrow rings for difficult years, cold or dry or dark. And in some rings, something else. A chemical signature left by volcanic aerosols that, in the years following a large eruption, dimmed the sun slightly and cooled the growing season. These volcanic signatures in tree rings have allowed scientists to build a remarkably precise record of eruptions going back thousands of years. Eruptions that happened before human records, Before written history, before anyone alive today, or anyone their ancestors knew had ever existed, the trees recorded what the historians could not. A bristlecone pine in the White Mountains of California, one of the oldest living organisms on Earth, approaching 5,000 years of age, carries in its rings the signatures of eruptions that happened during the Bronze Age. Eruptions that disrupted the climates of ancient civilizations. That may have contributed to crop failures and migrations and the falls of kingdoms. And the tree recorded all of it, quietly, in the width and chemistry of its annual layers, not knowing it was keeping history. Picture that tree gnarled, slow-growing, battered by millennia of high-altitude wind, standing on a rocky slope in the early evening light. It was old when the Roman Empire was young. It was already ancient when the first European ships reached the Americas. And inside it, written in wood, is a record of volcanic winters and volcanic springs, and the slow recovery of summers that followed them. The oldest trees on Earth are also some of its most detailed historians. They simply write in a language we are only recently learning to read. The warmth that rises from a lava field at night reaches for you before you see it. Active lava surfaces those freshly cooled but still radiating. Days or weeks after a flow release, heat upward in waves that become perceptible at a distance. Not the searing, dangerous heat of an active flow, but a gentle, ambient warmth that the skin registers before the eyes understand what is producing it. Walking toward such a surface in the darkness, you would feel it a soft increase in temperature, a change in the quality of the air above the rock, a warmth that seems to come from below rather than from any direction. Geologists and volcanologists who do fieldwork on lava fields at night describe this warmth with a consistency that suggests it is not merely physical but somehow effective. It feels, they say, like approaching something alive, not threatening, simply present in a way that cold rock is not. The lava field has not entirely finished being lava. It remembers what it was, and that memory radiates outward into the dark. In the hours before dawn, in the cooling of the night, this radiant warmth from a lava field can be felt even when no light is visible, the surface too dark in the darkness to see, but the heat arriving ahead of the light, announcing the field before you reach it. This is one of the Earth's most ancient forms of communication. Heat, moving outward from a warm body into a cooler space. The physics of it is simple. The sensation of it, in the dark, on a hillside of cooling lava, is something else entirely. Even the ground reaches toward warmth. Even the Earth, in its own way, leans toward connection. And you, resting now, are part of that same slow physics, warm among the dark, radiating gently into the night around you. Every strand of your DNA carries an element that rose through volcanic rock to reach you. Phosphorus is essential to life in a way that goes beyond nutrition. It is structural, the backbone of the DNA, double helix, the long spiraling ladder that carries every instruction your cells have ever followed, is made of phosphate groups. Each one a phosphorus atom bonded to oxygen atoms, linking the rungs of the ladder in a chain that runs through every cell of every living thing on Earth. Without phosphorus, the molecule that carries biological information cannot exist. Phosphorus arrives in the biosphere through weathering the slow dissolving of rock by rain and the chemistry of roots and soil organisms. And the rock that weathers most readily into bioavailable phosphorus is volcanic rock. Basalt, in particular, releases phosphorus as it breaks down. The volcanic soils that make tropical islands so extraordinarily productive are productive, in part, because they are still releasing phosphorus, still giving to the roots above them what the eruption put there millions of years ago. The phosphorus in your DNA has traveled a long road. It was in the mantle. It rose in magma. It cooled into basalt. It weathered out of that basalt over thousands of years. It dissolved into groundwater. It was absorbed by a plant. It passed through some number of other organisms before it arrived in the food that built your body. And now, It is in you, in the molecule that makes you continuous with every other living thing that has ever existed, in the structure that carries the instructions for your own particular self. The volcano did not know it was building toward you, but here you are assembled, in part, from what the earth gave up. Magma rises, not because it is pushed, but because it is lighter than everything around it. This is one of those facts that arrives quietly and then continues to grow in the mind, long after the first hearing. Magma does not need an explosion to move. It does not require a pump or a piston, or a dramatic triggering event. It rises the way a bubble of air rises through water, simply because it is less dense than the medium it is moving through, and the universe, in its patient way, always allows lighter things to rise. Partially molten rock in the mantle is less dense than the solid rock surrounding it. The melting itself reduces density, and the dissolved gases in the magma reduce it further. So, the magma rises, millimeter by millimeter, year by year, following the path of least resistance through fractures in the overlying rock, pooling where it cannot immediately continue, accumulating over thousands of years until the accumulated mass and pressure finally reach a surface. There is something deeply settling about this mechanism. The volcano is not driven by violence, fundamentally. It is driven by buoyancy, by the simple physical preference of lighter things for higher places. The same force that lifts a bubble, that rises warm water above cold water in a still lake, that carries wood to the surface of the ocean, that same gentle, universal tendency is what ultimately drives the magma from the mantle to the crust. The most dramatic landscapes on Earth were made by one of the most ordinary forces in physics. What rises because it is ready to rise, because the conditions have made it lighter than what holds it down. There is no forcing. There is only the natural direction of things, followed patiently for as long as it takes. From space, a volcanic eruption looks like the Earth is simply thinking. Satellites observing Earth from orbit have captured the moment of major eruptions, many times the sudden appearance of a white or grey plume rising from a point on the surface, spreading as it gains altitude, forming a wide, pale canopy at the height where the column's energy is finally exhausted and the material begins to spread horizontally. From orbit, at the scale of the whole planet, this does not look dramatic. It looks almost gentle, a small smudge of pale material, slowly widening against the blue and brown and green of the globe below. The Hunga Tonga eruption of 2022 was captured in extraordinary detail by weather satellites. The circular shock wave, expanding across the Pacific in concentric rings, visible in the water vapor data, as a perfect circle growing outward from a single point, crossing thousands of kilometers of ocean in the space of hours. It looked, in those satellite images, like the planet had been struck by something and was ringing, like a bell disturbed at its center, the disturbance spreading outward in mathematically perfect circles. But the eruption was not a strike from outside. It came from within. The planet was not struck. The planet rang itself, produced the disturbance from its own interior, and sent it outward in all directions. A thought, arising from within, spreading outward, reaching everywhere. The planet thinks in geological time, in processes too slow and too large for any human life to contain. But occasionally, in the moment of an eruption, in the ring of a pressure wave crossing an ocean, something of that thinking becomes briefly, beautifully visible. And from far enough away, it looks like nothing more than a quiet breath. The gentlest kind of volcano is measured not in ash clouds, but in footsteps. A shield volcano, in its quietest phase, does not announce itself. It seeps. From fissures in the ground, long cracks in the Earth's surface that open along the flanks of the volcano with minimal drama. No explosion, no column of ash lava, simply wells up and begins to flow. Slowly, spreading outward across the existing surface in thin sheets, covering the ground the way water covers a floor when a pipe leaks gradually, without urgency, following the slope. These fissure eruptions are, in geological terms, among the most productive. The lava that has built the ocean floors, that has constructed the vast basaltic plains of the Luna Maria, that has produced the enormous flood basalts of the geological record, all of it came from fissures, not from cone-shaped central vents. The gentle and the spreading, not the dramatic and the tall. Walking near an active fissure eruption at a careful, safe distance, the experience is surprisingly calm. The lava moves at walking pace or slower. The sound is a low, continuous crackling. The heat is present but not immediate at a respectful distance, and the smell, that faint mineral smell of fresh basalt and trace volcanic gases, is the smell of the earth opening itself, of new material arriving from below, joining the surface of the world for the first time. This is most of what volcanism is, across most of the planet's history. Not catastrophe, simply the earth, opening slightly, adding to itself, closing again. A whisper, not a shout. A slow addition, not a subtraction. Most of what the earth has ever made was made gently. The volcanic springs of Iceland warm not just bodies, but something older and harder to name. The tradition of gathering in geothermally heated water in Iceland is ancient, predating the settlement of the island by Norse people, who arrived and found the hot springs already there, already inviting, already doing what hot springs do. In the saga literature, decisions were made at hot springs. Disputes were settled. Meetings that mattered happened beside the steam and the warm water, in that particular quality of ease that comes from being warm in a cold landscape. The modern geothermal pools of Iceland, from the famous Blue Lagoon to the neighborhood pools that every Icelandic town maintains as a public amenity, heated by the same volcanic resource, continue something very old. People go to them not primarily for hygiene or sport, but for the same reason people have always gone to warm water in cold places: to slow down, to be warm together, to have the kind of conversation that only happens when the body is at ease and the air is cold and the steam is rising, and there is no particular reason to leave. The water in an Icelandic pool has passed through volcanic rock. It carries dissolved minerals from that rock, silica, sulfur, trace elements that have given it a particular quality, a slight silkiness, a mineral presence on the skin. You are bathing in something the earth produced, something the earth is still producing. The warmth is the same warmth that moves in the mantle, slowed, cooled to something comfortable, delivered to the surface through a system of pipes and stone. Even as you rest right now, somewhere in Iceland, someone is sitting in volcanically heated water in the open air, looking at a dark sky, saying nothing, needing nothing. The earth is warming them, and they know it, and it is enough. The iron-dark lava of some eruptions absorbs light the way deep space does. Fresh basaltic lava, the kind that flows from shield volcanoes and fissure eruptions, the thin and freely flowing kind, cools to a surface that is among the darkest natural materials on Earth. Not dark grey, not charcoal, not the darkness of wet pavement or deep shadow. Genuinely, almost profoundly dark. A surface that reflects so little light that it seems, in certain conditions, to have less presence than the space around it, to be a hole in the landscape rather than an object in it. This darkness comes from the mineralogy. Basalt is rich in iron and magnesium, and poor in the silica that gives lighter rocks their color. And fresh basalt, before weathering has had any time to alter its surface, before any lichen has arrived, before any rain has left, any mineral deposit is as dark as volcanic glass can be. In the Hawaiian language, there are words for different kinds of lava surface that encode this quality of darkness, among other qualities the texture, the feel underfoot, the sound it makes. Language developed to describe something so present in daily experience that ordinary words were insufficient. Standing on a fresh lava field in bright sunlight, the contrast between the blazing sky and the almost light-absorbing ground beneath your feet produces a quality of visual experience that is genuinely strange. The ground is there solid, real, warm, and yet it seems to take the light and keep it, to absorb without reflecting. Dark enough to feel like the sky's counterpart. Dark enough to make the stars, when they come, seem not far away but simply on the other side of something. Scientists who listen to volcanoes long enough begin to know them by name. Not officially, not in any protocol or published paper, but in the way that people who spend years with something come to know it individually. The volcanologists who monitor Kilauea, who have sat with its data through quiet years and active ones, who have watched its lava lake drain and refill and drain again, who have driven its roads in the dark to check on instruments. After a sudden change in the tremor signal, these people speak of the volcano with a familiarity that has no scientific name, but is clearly something beyond professional relationship. They know what is normal for it, what an unusual reading looks like against the baseline of what it usually does. They have a feel for its rhythms that accumulated not from any single observation but from 10,000 observations stacked across years. The way a musician develops an ear not from studying music theory but from listening. This kind of knowledge, attentive, patient, long accumulated, personal, in the sense that it belongs to specific people who earned it through specific years, is one of the most quietly valuable things science produces. It cannot be fully transferred in a paper. It lives in the people who developed it. And it means that the people who monitor a volcano are not just reading instruments. They are in relationship with something vast and geological, and, in their particular knowing of it, deeply familiar. The volcano does not know it is known, but it is known. And the knowing, on both sides of that asymmetry, is real. The city of Rome was built on what a volcano left behind. The hills of Rome, the 7 hills on which the ancient city was founded, whose names became legend, are not random topographic features. Several of them are the remnants of ancient volcanic activity. The tufa stone that built Rome's earliest structures quarried from the surrounding landscape, cut into blocks, stacked into walls and arches and temples, is volcanic. It is compressed volcanic ash, welded together by heat into a material light enough to quarry easily but durable enough to build with. The Roman builders did not know what tufa was, in any geological sense. They knew it was workable. They knew it cut cleanly and held its shape and was available in abundance from the hills around them. They quarried it and shaped it and stacked it into the foundations of a civilization. Beneath the streets of modern Rome, the volcanic tufa continues. The same stone, in geological continuity, beneath 2,000 years of history. Beneath the layers of civilization that accumulated above it. Republic, empire, medieval, Renaissance. Modern, the volcanic stone simply continues to be what it is. The oldest layer. The foundation beneath the foundations. The eternal city sits on volcanic rock. Its antiquity is, in part, the antiquity of what the earth left there before anyone arrived to build on it. Even the most human of things, a city, a civilization, 2,000 years of unbroken habitation rests on something the earth made first. We do not build on bedrock. We build on the earth's own history. And the history, patient and volcanic, holds us up. In the oldest stories, the mountain always goes back to sleep. Every culture that has lived beside a volcano has developed a story about it. Not always the same story. The details change. With the landscape, the language, the particular character of the mountain, and the people who grew up in its shadow. But something persists across all of them. Something consistent enough to notice. The mountain is alive. The mountain has moods. The mountain, when it erupts, is expressing something: anger, grief, abundance, renewal, and when it quiets, it is not defeated or dead, but resting. Return to a state of patience that preceded the eruption and will outlast the memory of it. The story, in almost every tradition, does not end with the eruption. It ends with the mountain going quiet again, with things returning, with life reasserting itself on the slopes, with the people who remained, or who came back, finding the soil richer than before. The Javanese people who live on the slopes of Merapi one of the most active volcanoes in the world, which has erupted dozens of times in recorded history, have maintained a continuous relationship with the mountain for centuries. There are ceremonies, there are offerings, there are designated keepers of the mountain's relationship with the communities below, and there is a cultural understanding, encoded in practice and story, that Merapi is not an enemy, it is a neighbor, a powerful one, requiring respect and attention, and the particular kind of relationship that acknowledges something as greater than yourself without being diminished by that acknowledgement. This is not naivety. It is a sophisticated orientation toward living with something you cannot control. The mountain will do what it does, and the people will remain, and the story will continue. It has always continued, across every eruption, every loss, every season of quiet that followed. The mountain goes back to sleep, and the people tend their gardens in the rich volcanic soil. And this has been true for as long as both have existed. After a great eruption, the ocean carries the evidence for years. The pumice that erupts from a submarine or coastal volcano does not all beach immediately. Much of it is carried by ocean currents, the great, slow rivers of the sea, driven by temperature and salinity, and the rotation of the Earth across thousands of kilometers of open water. Pumice from the 2012 Havre Seamount eruption in the Kermadec Arc was traced, by satellite and by ships, across thousands of kilometers of the Pacific Ocean over the following years. Pieces of it reached the shores of Australia, of New Zealand, of distant islands that had no connection to the eruption except the current. And on those pieces of pumice, as noted earlier, life traveled. But the pumice itself also carried information. Scientists who collected and analyzed pieces of the Havre pumice were able to reconstruct details of the eruption, its temperature, its gas content, its explosive character from the microscopic structure of the glass. The pumice was not just a raft, it was a record. Every piece of floating volcanic rock drifting across the ocean is a message from the seafloor encoded in the structure of its bubbles, in the chemistry of its glass, in the organisms that chose it as a vessel. A message that travels at the pace of currents, arriving at distant shores months or years after it was sent, carrying everything the eruption put into it. The ocean is patient enough to deliver these messages without hurrying, and the shores that receive them are richer for what arrives. There are places inside the Earth where rock is neither one thing nor another. The zone of partial melt, that region of the upper mantle where conditions of temperature and pressure are precisely intermediate between solid and liquid, is one of the most conceptually difficult features of the Earth's interior, not because the physics is complicated, but because it requires holding in mind a material that does not fit the categories ordinary experience provides. It is not liquid, it flows, but slowly, far more slowly than any fluid you have ever encountered. It is not solid. It deforms under sustained stress, yielding to pressure over geological timescales, moving through the mantle in the slow convective loops that drive plate tectonics. It is, genuinely, in between a zone of ambiguity where the boundary between states of matter becomes a region rather than a line. In this zone, small pockets of true melt exist, droplets and threads of fully liquid rock, distributed through a matrix of solid crystal, like moisture distributed through a dense sponge. Under the right conditions, these pockets connect, and the melt begins to move, percolating upward through the solid matrix the way water percolates through soil, collecting and concentrating until it forms a coherent body, a nascent magma, beginning its long rise toward the surface. The beginning of every volcano is here, in this zone of in-between, in the quiet ambiguity of rock that is both things at once, solid enough to hold the planet's structure, liquid enough to eventually become what rises. The Earth does not commit sharply to categories. It holds gradients, maintains ambiguities, and from those ambiguities, slowly, mountains rise. The darkest lava makes the stars look close. On the summit of Mauna Kea, the Hawaiian Shield volcano, whose peak, at nearly 4,000 meters, rises above most of the Earth's atmosphere. The world's most powerful astronomical observatories sit on volcanic rock, not by coincidence. The summit was chosen for what volcanic geography provides: extreme altitude, clean and stable air, the absence of the light pollution that gathers around human settlements, and the particular quality of darkness that a remote volcanic peak provides on a moonless night. The rock beneath the observatories is basalt, dark, ancient, quiet. The volcano last erupted on Mauna Kea's summit more than 4,000 years ago. The mountain is, in its upper reaches, cold and still and as close to a stable platform as the Earth's surface offers, and the darkness there, on a clear night, is the darkness that makes the universe visible. Astronomers who work on Mauna Kea describe the night sky from the summit with the particular reverence that scientists reserve for moments when reality exceeds what they thought they knew. The Milky Way is not a faint smear at altitude. It is a structure, a thing with depth and texture, and the sense of genuine three-dimensionality. The galaxy showing itself as a galaxy rather than as background. The stars are points, not the soft blurs that atmosphere and light pollution produce at lower elevations. From a volcanic peak, in the dark, the universe presents itself. The Earth lifted this mountain from the ocean floor over hundreds of thousands of years. And now, on its summit, we use it to see further than we can see from anywhere else. The volcano that rose from the deep gave us the high place from which to look. Bacteria have been found living inside volcanic rock, on chemistry alone. In the basaltic crust beneath the ocean floor, not at the surface, not in the warm water near vents, but inside the solid rock itself. In microscopic fractures and pore spaces, microorganisms have been found living in conditions that, by most prior definitions, would have precluded life entirely. No light, no organic matter from the surface, no connection to the world above, just rock and the chemical energy available from the reactions between that rock and the small amount of water that percolates through it. These organisms, mostly bacteria, some archaea, derive their energy from ion oxidation, from hydrogen produced by the reaction of water with olivine, from the slow chemical transformations of the rock around them. They grow extraordinarily slowly. Some are thought to divide only once every 10,000 years, a reproductive rate. So slow it is almost impossible to reconcile with any intuitive sense of what living means. And yet, they are alive. They maintain themselves. They respond to their environment. They have been doing this, in the rock, for perhaps millions of years. The discovery of these organisms and the ongoing discovery of similar life in deep mines, in subsea floor sediments, in places that seemed geologically sterile, has fundamentally changed the estimate of how much life exists on Earth. The deep biosphere, as it is called, may contain as much carbon as all the life on the surface. There is more life in the rock than we knew, more life in the dark, more life in the slow, chemical quiet of the Earth's interior than anyone imagined before we learned to look. Life, it seems, does not need much. It needs chemistry and time and the patient warmth of the Earth. It finds the rest itself. The perfect cone of a stratovolcano has been dreamed about for as long as humans have dreamed. There is something in the shape that the mind responds to before it knows why. The symmetrical rise from the surrounding landscape, the narrowing toward the summit, the suggestion of a point that draws the eye upward. It is one of the most recognizable silhouettes in the world, one that appears in the art of cultures that never communicated with each other, in paintings and woodcuts and drawings spanning centuries and continents. Hokusai's 36 views of Mount Fuji, that series of woodblock prints in which the perfect cone appears and reappears in different seasons, different weathers, different distances, always itself, always present, always slightly different, captured something that Japanese artists had been responding to for centuries, before Hokusai, and that artists have continued responding to ever since. The mountain does not change across the series. Everything around it changes. and the mountain remains, observing the changes from its height, wearing its snow like a patient crown. The stratovolcano's cone is built by alternating layers of lava and ash, each eruption adding something, building upward as well as outward. The viscous lava of these volcanoes, unable to spread as freely as the thin basaltic flows of shield volcanoes, instead piling closer to the vent, building height. The symmetry is not perfect in geological reality. It is eroded by weather, scarred by collapse, complicated by secondary vents. But from a distance, from the angle at which the human eye tends to encounter mountains, it reads as symmetry. And the mind, encountering that shape against a sky, responds with something that is very close to recognition, as if the cone were familiar, as if the mountain were something we had known before we knew it. The most isolated places on Earth are also the most biologically astonishing. The volcanic islands of the Central Pacific Hawaii, the Galapagos, the Azores, Tristan da Cunha, are among the most remote pieces of land on the planet. Separated from any continent by thousands of kilometers of open ocean, they were colonized by life that arrived by wind, by wave, by the bodies of birds, and the roots of floating wood. Each arrival was an accident. Each establishment was improbable. And yet, on each of these isolated volcanic islands, life did not simply survive. It diversified. In the absence of the competitors and predators that would have constrained it on a continent, the organisms that arrived found open ecological space and over millions of years filled it. Darwin's finches on the Galapagos, the birds whose variation helped him understand natural selection, are the famous example. But the same pattern holds everywhere these islands have been studied. Insects that arrived as a single colonizing species became dozens of species, each adapted to a slightly different niche. Plants evolved into forms unlike any of their relatives elsewhere. The volcanic island is not just a piece of ground. It is an experiment, isolated, controlled in the rough sense that islands provide, running for millions of years, an experiment in what life does when given space and time and the particular conditions of a volcanic soil. What it does is diversify. What it does is become more, not less. Isolation, given enough time, produces richness, and the volcanic earth, rising from the ocean in its patient way, provides the conditions for that richness to begin. The calcium that builds your bones was carried here by the same deep processes that feed volcanoes. Calcium is one of the most abundant elements in the Earth's crust present in the rock, dissolved in groundwater, cycled through the ocean, absorbed by marine organisms that build shells and skeletons from it, deposited on the sea floor when those organisms die, subducted at the edges of plates, released by metamorphism and volcanic activity back into the crust and the ocean. The calcium cycle is one of the Earth's long, slow metabolic loops, a planetary process operating over millions of years, moving calcium from one form to another, from one place to another, keeping the element available to life in the concentrations that life requires. Your bones contain calcium that has been through this cycle many times, calcium that was at some point in its history part of a volcanic rock, part of the seafloor, part of a shell, part of the ocean, part of the soil, part of food, part of you. The hardness of bone, that quality that makes it a scaffold strong enough to hold a body upright, to protect the organs within, to allow the particular kind of motion that mammals are capable of, that hardness, is calcium phosphate. Two elements, both cycled through the earth by geological and biological processes, both arriving at you through long, slow, planetary paths. Even as you rest right now, the calcium in your skeleton is doing what it has always done, holding your body's architecture together quietly, in the dark, asking nothing. The earth gave you your bones, and your bones have been holding you up, faithfully, ever since. A pressure wave from a great eruption can circle the earth like a slow, planetary breath. When Hunga Tonga erupted in January of 2022, The atmospheric pressure wave it generated was detected by weather stations on every continent, not once, but multiple times. As the wave traveled around the Earth and returned to its origin and continued outward again, like a ripple that does not stop at the edge of the pond, but curves back around the curve of the world and keeps going. Meteorologists, watching their barometers that day, saw the needle move a small, unmistakable deflection, the atmosphere pressing slightly and then releasing, and knew immediately what they were seeing. Some of them described a feeling they could not entirely explain. Not alarm. Something closer to awe. The knowledge that the instrument on their desk, in their office, in their city, was registering something that had begun on the other side of the planet hours before and had traveled through the air above all the geography between. The wave circled the Earth at least 4 times before it faded below the threshold of detection. 4 circuits of a planet, carried in the air, driven by a single moment of volcanic energy released from a seamount in the South Pacific. The atmosphere carried it. The atmosphere that began as volcanic gas, that was transformed by life over billions of years, that now holds weather and breath and the particular blue that makes the sky. That same atmosphere carried the memory of the eruption around the world, again and again, until the energy finally dissipated into the vast warmth of the air. The Earth breathed out, and the whole sky felt it. A raft of pumice can cross an ocean, carrying hundreds of species, and not one of them knows it is traveling. The 2019 Tonga pumice raft, one of the largest recorded, stretching across nearly 150 kilometers of ocean surface, was studied in extraordinary detail as it drifted toward Australia over the following months. Scientists joined it by boat and by satellite, sampling its passengers, cataloguing the diversity of organisms that had colonized the floating volcanic glass within weeks of its formation. What they found was a living community of genuine complexity. Not just the barnacles and bryozoans that colonize floating debris generally, but polysheet worms, mollusks, echinoderms, crustaceans organisms representing dozens of phyla, hundreds of species, an entire miniature ecosystem organized around a temporary volcanic island, the size of a large city, floating and drifting, and slowly, over months, dispersing as individual pieces broke off and beached on distant shores. Each piece that beached carried its passengers to a new coast. Some of those organisms established themselves, some did not. But the attempt was made the improbable, unintentional, volcanic-powered dispersal of life across an ocean, happening in the same way it has been happening for hundreds of millions of years. The pumice does not know it is a vessel. The organisms do not know they are passengers. The ocean does not know it is a highway. And yet, the journey happens, has always happened, will happen again the next time a volcano erupts near open water and the wind is right and the currents are running. The Earth has always been moving life around. It does not ask permission. It does not plan. It simply erupts and floats, and the living things find each other on the far shore. The Earth is not finished making itself, and right now, somewhere, it is adding to what exists. This is not a metaphor. At this exact moment, on the southeastern coast of the big island of Hawaii, lava from Kilauea's ongoing activity may be entering the ocean and extending the island's coastline by a small, measurable amount. On the mid-Atlantic ridge, magma is upwelling along a rift that runs the length of the Atlantic and pushing the seafloor outward by the width of a fingernail this year, and the same amount next year, and the same amount the year after. In Iceland, a fissure eruption may be adding new basalt to the surface of an island that has been growing intermittently since it first broke the ocean surface 16 million years ago. The making of the world is not a past event. It is a present one, continuous, patient, operating at scales of time and space that make it invisible to any individual life and yet real, verifiable, measurable in the accumulated record of geology and in the data streaming from instruments mounted on volcanic slopes right now, tonight, while you rest. The planet you are resting on is not a finished thing. It is a work in progress. A process that began 4.5 billion years ago and has not paused since and will not pause after you are gone. The mountains that will exist in 10 million years are already being prepared in the mantle. The ocean floors that will spread in 50 million years are already beginning to rift. The volcanic islands that will rise from the Pacific in 100 million years are already being warped by a mantle plume whose heat is already in motion. You are resting in the middle of a creation that has no end. And that, somehow, is not frightening. It is the opposite of frightening. It is the most patient comfort the universe offers, the knowledge that the making continues quietly without needing you to do anything at all. The first volcanic eruptions happened before there was anyone to be frightened of them. On the early Earth, in the first few 100 million years after formation, when the surface was still largely molten, when the crust was thin and constantly being broken and remade, volcanism was not an event. It was a condition. The entire planet was volcanic in the way that a flame is hot, not in places, everywhere, all the time. There were no mountains yet in the sense we mean the word. There were no oceans, though the first water was already arriving as steam from volcanic outgassing and beginning to condense. There were no continents, only thin, unstable patches of crust floating on a planet that was still, in many places, glowing. The volcanism of the early Earth built everything that came after. It exhaled the atmosphere. It contributed to the filling of the ocean basins. It produced the first stable crust thick enough to persist the ancient cratons that still form the cores of the continents. It created the conditions in which the chemistry of life first became possible: warm, mineral-rich water, energy gradients between hot and cold, the particular combination of elements that life would eventually learn to use. Everything that exists on the surface of this planet, every mountain, every ocean, every grain of soil, every organism, including the one reading this, is downstream of those first, total, world-making eruptions. The early Earth did not know what it was making. It simply followed the physics of its own conditions, step by step, eruption by eruption, atmosphere breath by atmosphere breath, and eventually, impossibly, the conditions for something that could wonder about it arose. You are what the early Earth's volcanism eventually produced. Not directly, not simply, but in the long, branching, improbable chain of consequence that connects the first magma ocean to this moment. You are here. The volcano did not know it was making a world that would one day ask questions about it. But here you are, asking. A lava field at night holds its own light and keeps it long after the source has gone. In the hours and days after a lava flow has stopped moving and the surface has cooled enough to walk on, something persists beneath. The interior of the flow, insulated by the hardened crust above, retains its heat for weeks, sometimes months. In the dark, from certain angles, this retained heat becomes visible, not as flame, as a deep internal glow, red and amber, seeping through cracks in the surface, pulsing slightly when the wind moves the thin crust and shifts the air, reaching the still warm interior. A lava field glowing from within, at night, in the absence of any other light source, is one of the most quietly extraordinary things the natural world produces. The surface looks solid. It is solid, you could walk on it, if the crust is thick enough, and yet it glows. From below, from the memory of what it recently was, from the heat it has not yet finished releasing into the cooler world above it. It looks like thinking. It looks like a mind working beneath a still surface. It looks like the earth dreaming. And perhaps that is not entirely metaphor. The lava was, hours or days ago, connected to the deep interior of the planet, part of a system of heat and pressure that extends all the way down to the boundary between the mantle and the core. It carried that connection to the surface and is now, slowly, releasing it, giving it to the night air, cooling, degree by degree, toward the ambient temperature of the world around it. This is what warmth does in the physics of the universe. It spreads. It seeks equilibrium. It moves from where it is concentrated to where it is not, until everything is the same temperature. The lava is returning to the world's temperature, giving its heat away, and in giving it away, it glows. Even as you rest right now, somewhere a lava field is doing this, glowing from within, in the dark, releasing its warmth into the night, slowly becoming the same temperature as everything around it. Warmth given away is not warmth lost. It is warmth shared. Every volcano that has ever existed is still part of the world, in one form or another. The lava that erupted and cooled became rock. The rock that weathered became soil. The soil that nourished roots became food. The food became bodies. The bodies, in time, returned their elements to the soil and the ocean and the air, and the cycle continued. The same atoms, in different arrangements, in different forms, passing through one living thing and then another, through water and cloud, and sediment and rock, and eventually back into the mantle, where they will be heated and erupted again. Nothing the earth has produced has left the earth. Every eruption that has ever happened is still here, its material dispersed and transformed and incorporated into the ongoing world, but present. The first eruption, 4.5 billion years ago, is present in the iron, in your blood, in the nitrogen, in the air you are breathing, in the calcium holding your body upright. The ancient volcanoes did not end. They became, and the becoming never stops. It is simply slower, in most of its current forms, than any single lifetime can observe. Slow enough to feel like permanence. Slow enough to be trusted. Slow enough to rest on. The ground beneath you is old and patient, and made of everything that came before, and it will continue to be remade, slowly, long after every name currently given to anything has been forgotten and replaced by names we cannot imagine. This is not a melancholy thought. It is a settling one. The kind of thought that makes the body heavier and the breath slower, and the concerns of the day smaller and more manageable. You are part of this. You have always been part of this. You will, in your own time and in your own way, continue to be part of this. Nothing is lost. Everything is in the middle of becoming something else. Right now, in the deepest quiet, the earth is listening to itself. Seismometers placed on the ocean floor, on volcanic peaks, in deep boreholes drilled into stable ancient rock, all of them recording, continuously, the low vibration of a planet in motion, the hum of the ocean against every shore, the slow settling of mountain ranges, the faint tremor of magma moving in channels far below, the pulse of tides distorting the shape of the solid earth by centimeters twice a day, the planet breathing in and out with the pull of the moon. All of this is happening right now. All of it, simultaneously, on every part of the surface and inside every layer of the interior. From the thin crust at the surface to the liquid iron of the outer core turning in the dark at the center of the world. The instruments record it. The data accumulates. Scientists read it in the morning and add it to the long, patient record of a planet taking its own pulse. And you are on the surface of this, resting on it, your body's own warmth in contact with the ground beneath you, a thin, imperceptible exchange of heat between your warmth and the Earth's. Your breath moving in the same atmosphere that the Earth has been exhaling into for 4 billion years. Your heartbeat a small additional vibration in a world already full of vibrations too slow and too large for you to feel. You are not separate from what the Earth is doing. You are one of the things the Earth is doing. One small warm breathing part of a planet that has been making warm breathing things for the last 4 billion years and has not stopped yet. You are resting on a planet that is still making itself. This is the last fact and the first fact and the only fact in the end. Everything else, every detail of lava and magma and caldera and vent and pumice and pillow, basalt and volcanic soil and geothermal spring, everything else is just a different way of saying this one thing. The Earth is not finished. It has never been finished. It will not be finished for longer than any number you care to name. And in its unfinishedness, In its continuous patient making and remaking, it has produced among everything else, it has produced the conditions for you to exist, for you to lie here, in this particular moment, on this particular night, breathing this particular air. The volcanoes made the ground made the soil made the food made the body, and here you are, inside it warm and breathing and, for now, still. You do not have to do anything with this. You do not have to hold it or understand it or remember it in the morning. The earth will continue whether or not you remember. The magma will move. The crust will shift. Somewhere in the Pacific, new land will arrive at the ocean's surface, dark and warm and unannounced, and begin the long process of becoming something a root can find purchase in. It has always been this way. It will always be this way. And you are, for this brief and specific and unrepeatable moment, here for it. Let the weight of your body settle now, all the way down. Feel the surface beneath you firm, patient, present. That surface connects, in an unbroken line of material, all the way down through the floor, through the foundation, through the soil, through the rock, through miles of ancient crust, to the place where the rock begins to warm, where the Earth's interior heat, 4.5 billion years old, still rises slowly toward you. It will not reach you tonight, but it is rising. It has always been rising, and the ground between you and it is solid and old and made of everything that has ever erupted and cooled and weathered and settled and become the world you live on. You are held by something very old. Outside, right now, the atmosphere is doing what it always does, moving slowly in the dark, carrying moisture from one place to another, holding the planet's warmth close the way a blanket holds a body's warmth. Somewhere in that atmosphere, particles from eruptions years and decades past are still drifting at altitude, still scattering light, still part of the long story of what the Earth has exhaled and what the sky has kept. The oceans are moving, slowly, in their deep currents. Water that has not seen the surface for 1,000 years is rising in some distant upwelling, cold and mineral-rich, carrying the patient chemistry of the deep. On the seafloor, pillow basalt is sitting in the dark, exactly as it cooled, waiting with the patience of rock for the slow movement of the tectonic plates to eventually carry it back to the mantle, where it will be remade. In Iceland, someone is in warm volcanic water, under a dark sky, saying nothing. In Hawaii, a lava field is glowing faintly from within, giving its warmth to the night. In the deep Pacific, a hydrothermal vent is breathing heat into the cold dark, and around it, in that warmth, something is living that has never needed the sun. And somewhere in the mantle, far below all of this, magma that will one day become a new island, or a new lava field, or a new piece of ocean floor, is moving slowly, without urgency, in a direction that is simply upward. All of this is happening right now, all of it, quietly, while you rest. The planet does not need you to do anything. It is tending itself, as it always has, in the dark and in the deep and in the warm places where the Earth's own fire rises gently toward the surface and arrives sometimes as something beautiful. Your breath is slower now. The thoughts are quieter. Whatever carried you into this evening is still there. But further away the way, a distant mountain is still there, even when the mist has softened it into something that barely distinguishes itself from sky. You are warm. You are held. You are resting on 4.5 billion years of patient making on ground that was once something else and will one day be something else again. But tonight is exactly what you need it to be. Solid. Still. Yours for now. The volcanoes are sleeping. The lava is cooling. The new land at the ocean's edge is hardening, quietly, into something that will hold. And you are here, inside this moment, which is small and warm and complete. Let the earth hold you. It has been holding things for longer than you can imagine, and it has never dropped one. Breathe slowly. Rest deeply. The fire beneath the ground is patient and ancient and still. And so, now, are you. I hope you sleep well and dream softly. Good night.